Look around. That chair you might be sitting in, the desk holding your screen, the floor under your feet. They all seem perfectly still. Our everyday lives teach us that things can, and do, stop moving. A rolling ball grinds to a halt. A spinning top eventually wobbles and falls. Stillness feels like the default, natural end state for everything. For a long time, scientists thought this intuition was true on the most fundamental level. They had a simple, elegant dream: to cool something down so far that every single atom, every particle, would come to a perfect, silent stop. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. They called it absolute zero, the ultimate state of stillness, the final frontier of cold. It was this beautiful idea of perfect tranquility, where the chaotic dance of atoms would finally just cease. But as they chased this dream, as they pushed technology to get colder and colder, they didn't find the quiet end of motion they were looking for. Instead, they stumbled upon a bizarre and unbreakable law of the universe. A law that says nothing ever truly stops. Even at the coldest temperature possible, in the darkest, emptiest vacuum of space, reality is locked in a state of perpetual motion. The universe, it turns out, fundamentally resists being still. The dream of absolute stillness. To get why this is such a shock, you first have to understand the dream it shattered. The quest for absolute zero wasn't just about making things cold, it was a journey into what temperature even is. For most of history, we didn't really get heat and cold. They were just qualities things had. But by the 18th and 19th centuries, a new picture was taking shape. Scientists started to realize that temperature isn't some mysterious property. It is motion. The heat you feel from a hot stove? That's the violent vibration of its atoms, smacking into air molecules, which then smack into your hand. The cold of an ice cube is just its water molecules being locked in a crystal, jiggling around way less energetically. Everything, from the air we breathe to the stars in the sky, is made of particles in constant, frantic motion. Hotter things have faster moving particles. Colder things have slower ones. So, temperature is just a measure of the average kinetic energy, the energy of motion of a bunch of atoms. This simple, powerful idea led to a logical question. What happens if you keep removing that energy? If heat is motion, what happens when you take all the heat away? Scientists in the 17th, 18th, and 19th centuries, playing with a new technology, gases, started to find clues. Researchers like Robert Boyle and Jacques Charles found that if you cool a gas down, its volume shrinks by a predictable amount. And this is where the first hint of an ultimate cold appeared. They noticed a pattern. For every degree Celsius you cooled a gas, its volume decreased by about 1/273rd of its volume at 0 degrees Celsius. So they did the math. If you kept cooling it, at what temperature would its volume, theoretically, shrink to zero? The answer was about -273 degrees Celsius. Now, obviously, a gas can't have zero volume. It would turn into a liquid and then freeze solid long before that. But the math pointed to a clear destination. There seemed to be a floor, a basement level to temperature, that you just couldn't go below. In 1848, the brilliant physicist William Thomson, later known as Lord Kelvin, formalized this. He proposed a new temperature scale, one based on this fundamental limit. He called that limit absolute zero. On his new scale, which we now call the Kelvin scale, this ultimate cold is 0 Kelvin. That corresponds to -273.15 Celsius, or about -459.67 Fahrenheit. For Kelvin, the logic was ironclad. If temperature is motion, then 0 Kelvin must be zero motion. It was the point where all thermal energy was gone. Atoms would stop vibrating, and everything would settle into a state of perfect, eternal rest. It was a beautiful, intuitive vision. The dream of absolute stillness was born. And with that dream came a race. The journey to absolute zero became one of the great adventures of physics. It was a brutal technological challenge, a step-by-step descent into unimaginable cold. Scientists built incredible machines to liquefy one gas after another, each time reaching a new record low. They conquered oxygen at 90 Kelvin, then nitrogen at 77 Kelvin. The next great challenge was hydrogen. The British chemist James Dewar finally succeeded in 1898, liquefying it at a frigid 20 Kelvin. Each step brought them closer. But one gas stubbornly refused to give in: helium. It was the last gatekeeper on the path to absolute zero. That final barrier was broken on a long summer day in the Netherlands. On July 10, 1908, after a grueling day of work, the Dutch physicist Heike Kamerlingh-Onnes and his team finally did it. They forced helium gas to condense into a clear liquid at just 4.2 Kelvin, a mere 4 degrees above absolute zero. Humanity now had a coolant that could get them a whisper away from the predicted point of perfect stillness. They fully expected to see the final proof of their dream. As they cooled things down, they thought they'd see atomic vibrations just fade away. But that's not what they saw. In 1911, while studying a mercury wire, Onnes saw its electrical resistance drop as expected. But then, at 4.2 Kelvin, it didn't just get low. It vanished. Completely. He called it superconductivity. This wasn't the gentle end of motion. This was something strange. It was the first clue that near absolute zero, the universe plays by a completely different set of rules. The quantum plot twist. For a while, the dream of stillness and the strange reality of superconductivity existed side by side. But as the 20th century unfolded, a new theory was being forged that would shatter the classical dream completely: quantum mechanics. Quantum mechanics rewrote the rules for the very small. It described a world that was fuzzy, probabilistic, and deeply weird. And buried in its math was the ultimate roadblock to absolute stillness, discovered by Werner Heisenberg in 1927. It's called the Heisenberg uncertainty principle. The uncertainty principle is one of the most mind-bending ideas in all of science. Simply put, it says you can't know certain pairs of a particle's properties with perfect accuracy at the same time. The most famous pair is a particle's position and its momentum, basically, where it is and where it's going. Heisenberg's principle states that the more precisely you know a particle's position, the less you can know about its momentum, and vice versa. This isn't because our tools are clumsy. It's a fundamental, built-in fuzziness to nature. Imagine trying to find a single electron. To see it, you have to hit it with something, like a particle of light, a photon. If you use a high-energy photon, you can pinpoint its position really well. But that photon gives the electron a huge kick, changing its momentum unpredictably. If you try to be gentle with a low-energy photon, you won't disturb its momentum much, but its long wavelength means you'll have no idea exactly where the electron is. It's like trying to find a tiny pebble by poking it with a giant beach ball. So what does this have to do with absolute zero? Everything. Let's go back to that classical dream. At absolute zero, a particle is supposed to be perfectly still. Its momentum is exactly zero. Not close to zero, but precisely zero. Well, if you know its momentum is perfectly zero, the uncertainty principle kicks in with a vengeance. If the uncertainty in momentum is zero, the uncertainty in its position must be infinite. That means a particle that is perfectly still would have no definite location. It would have to be everywhere in the universe at once, which is obviously nonsense. A particle can't be both perfectly still and have a location. The laws of quantum mechanics forbid it. So, a particle can never be perfectly motionless. It must always have a tiny, irreducible amount of motion. This minimum energy that a particle has, even at absolute zero, is called zero-point energy. It's the energy of existence itself. It's not heat you can remove by cooling. It's a fundamental quantum jitter that comes from just being a particle confined in space. Think of it like a guitar string. You can let the vibrations die down, but quantum mechanics says it never becomes perfectly straight and still. It's always humming with its zero-point energy. And this isn't just a quirky theory. It's a measurable reality with very real consequences. We see its effects all the time in the lab. For instance, zero-point energy is the reason why liquid helium refuses to freeze at normal atmospheric pressure, even when cooled to a fraction of a degree above absolute zero. Its atoms are jiggling with so much zero-point energy that they can't lock into a solid crystal. You have to put it under immense pressure, about 25 times normal atmospheric pressure, to force it to become solid. Another stunning piece of evidence is the Casimir effect, predicted in 1948. If you place two uncharged metal plates incredibly close together in a perfect vacuum, they will actually be pushed together by an invisible force. Why? Because the space between the plates restricts the kinds of virtual particles that can pop into existence from the vacuum's zero-point energy, while the unlimited space outside the plates doesn't have this restriction. This creates a pressure difference that pushes the plates together. This force was measured precisely in 1997, and it matched the predictions perfectly, proving that the energy of empty space is very real. The dream of absolute stillness wasn't just broken, it was proven to be impossible by the very nature of reality. The unreachable frontier and the restless universe. So, we can't have perfect stillness because of quantum mechanics. But there's another, equally profound reason it's impossible, one that comes from the grand laws of heat and energy themselves. The third law of thermodynamics. You've probably heard of the first two laws. The first is that energy can't be created or destroyed. The second introduces entropy, which is basically a measure of disorder. The second law says that things always tend to move from order to disorder. Your bedroom doesn't spontaneously tidy itself, right? Heat flows from hot to cold, not the other way around. The third law connects entropy directly to absolute zero. It says that as you approach absolute zero, a system's entropy, its disorder, approaches a minimum constant value. For a perfect crystal, that value is zero. This makes sense. At high temperatures, particles are zinging around with tons of energy in countless possible arrangements, high entropy. As you cool it, they slow down, and their arrangements become more limited, low entropy. At the theoretical point of 0K, everything would be in one, single, perfectly ordered state. Zero disorder, zero entropy. But the third law has a hidden sting in its tail. It implies that you can never actually get to absolute zero. To cool something, you need to put it in contact with something colder. But to reach absolute zero, you'd need a reservoir that is already at absolute zero, which is a catch-22. Even with super clever techniques, each step you take to remove that last little bit of heat gets exponentially harder. As you get closer and closer to 0K, the amount of work you have to do to extract the next tiny bit of energy becomes infinite. The universe demands an infinite price for perfect order. So, physics gives us a 1-2 punch against the dream of stillness. The uncertainty principle says perfect stillness is illegal at the quantum level. The third law says reaching the conditions for that stillness is practically impossible anyway. The finish line of the race to absolute zero will always be infinitely far away. And this isn't just some philosophical point. It's woven into the fabric of reality at every scale. At the quantum level, it's the zero-point energy that keeps atoms jiggling. Zoom out, and every atom is a whirlwind of motion. Electrons exist as clouds of probability, and the nucleus itself is a vibrating cluster of particles. Zoom out to our scale. The solid objects around you are a lie. They are mostly empty space, with atoms held in a lattice, each one vibrating furiously. The stillness you perceive is just an illusion created by averaging out the motion of trillions of atoms. Zoom out to the planetary scale. Our planet is spinning at 1,000 miles per hour, while hurtling through space at 67,000 miles per hour around the Sun. The Sun itself, with all of us in tow, is orbiting the center of the Milky Way at a staggering 500,000 miles per hour. And the galaxies aren't still, either. Our galaxy is part of a local group, all moving relative to each other, being pulled toward a gravitational anomaly called the Great Attractor. And on the largest scales, thanks to the Big Bang, nearly every galaxy is flying away from every other galaxy. The very fabric of spacetime is expanding. Even the emptiest vacuum of space isn't truly empty or still. It's a seething cauldron of quantum activity, a quantum foam. Thanks again to the uncertainty principle, pairs of virtual particles can borrow energy from nothing, pop into existence for a split second, and then annihilate each other. There is no quiet corner of the cosmos. There is no off switch. The fact that the universe is fundamentally restless, that nothing ever truly stops, changes how you see everything, from a block of ice to the vacuum of space. It's one of those ideas at the very heart of modern physics. If you enjoyed this journey from the simple dream of stillness to the bizarre reality of the quantum world, please consider liking this video and subscribing for more deep dives into the biggest ideas in science. So, we started with a simple idea. Make something cold enough, and it will stop moving. It was a dream pursued by brilliant scientists, a quest for a final, silent state called absolute zero. But as we got closer, reality turned out to be far stranger than anyone imagined. The laws of quantum mechanics forbid perfect stillness. A particle must always keep a minimum amount of motion, its zero-point energy, or it would violate the rules of its own existence. And the laws of thermodynamics show us that even if it were possible, getting there would be an infinite task. We've seen how this isn't just theory, but something with real, measurable consequences, like the strange behavior of liquid helium and the bizarre Casimir force. This perpetual motion isn't a bug in the system. It is the system. It connects the hum of a single atom to the expansion of the entire universe. It teaches us that stillness is the illusion. The universe isn't a static stage where things happen. The universe is the event. It's a process. It's a constant, unfolding, restless reality. And maybe there's a profound beauty in that. The universe is not destined for a quiet, frozen end. It is, and always will be, alive with motion. The impossible motion at absolute zero. Imagine the coldest possible place in the universe. A point of such profound cold that all the chaotic buzzing of existence just stops. We're talking about a temperature of -273.15 degrees Celsius, or -459.67 Fahrenheit. It's a theoretical floor to reality that scientists call absolute zero. For over a century, reaching this point was one of the biggest goals in all of physics. It was the finish line for the universe's thermal energy. The logic seemed simple, elegant, and totally compelling. The idea was this: temperature is just a measure of motion, the jiggling, vibrating, and colliding of atoms. Hotter means faster, more violent motion. Colder means slower, more sluggish motion. So, if you could just remove every last drop of heat, you'd end up with a state of perfect, eternal stillness. The death of all movement. Scientists dreamed of seeing it. They pictured a crystal of atoms frozen into a perfect, motionless lattice, a silent monument at the end of temperature. They raced to reach this ultimate cold, this final quiet. But when they got closer than humanity had ever been, to temperatures just billionths of a degree above absolute zero, they didn't find the stillness they were looking for. They found something that shouldn't have been possible. They found movement. It was a bizarre and unbreakable law of quantum mechanics, one that forces everything in the universe to move, forever. What they discovered wasn't the end of motion, but a ghostly, perpetual dance that can never be stopped. A faint, ever-present hum woven right into the fabric of reality. This is the story of a scientific quest that completely upended our classical view of the universe. It's the story of how the race to achieve perfect stillness led to the discovery of unavoidable, eternal motion. So how did scientists get it so wrong? And why is it that, even in the coldest, emptiest void imaginable, nothing ever truly stops? The classical dream. A universe of perfect stillness. To understand the revolution, you first have to understand the dream. And that dream was born from a very simple question. What is heat? For a long time, the best guess was that heat was a kind of invisible, weightless fluid called caloric. People thought it flowed from hot objects to cold ones, like water seeking its own level. A hot cup of coffee had a lot of caloric, an ice cube had very little. It was intuitive, it made a certain kind of sense, but it was also dead wrong. The big shift started in the late 18th and early 19th centuries, with thinkers like Count Rumford and later, James Joule. They showed that heat wasn't a substance at all. It was a form of energy, specifically, the energy of motion. This new idea, the kinetic theory of heat, was radical. It changed our understanding of temperature from a measure of some mystical fluid to a direct measurement of the average kinetic energy of atoms and molecules. Think of it like a microscopic mosh pit. In the air around you right now, countless trillions of nitrogen and oxygen molecules are careening about at hundreds of meters per second, smashing into each other billions of times every second. That warmth you feel on your skin? That's the sensation of this relentless atomic bombardment. In a solid, like the chair you're sitting on, the atoms aren't flying around freely, but they're not still either. They're locked into a crystal lattice, vibrating intensely in place, like tiny springs that are constantly twitching. Hotter just means a more frenzied mosh pit. Colder means the mosh pit is calming down. From this elegant new understanding, a profound conclusion followed. If heat is motion, then what happens if you remove all the heat? The answer seemed obvious. All motion must stop. This hypothetical endpoint was given a name: absolute zero. On the Kelvin scale, which is what scientists use, this is 0 Kelvin. The point where all thermal energy has been drained from a system. The concept was intoxicating. It defined an ultimate limit to the physical world. The third law of thermodynamics makes it official, stating that as you approach absolute zero, the entropy, a measure of disorder of a perfect crystal, approaches zero. In simple terms, at absolute zero, a perfectly formed substance should be in a state of perfect order, with its atoms locked into a single, unchangeable, and completely motionless arrangement. And so, the race began. It was a scientific odyssey as challenging as the race to the geographic poles. In the late 19th century, labs across Europe became battlegrounds in the quest for cold. The challenge was immense. To get colder, you had to find ways to rob atoms of their energy. The main method was to turn gases into liquids. Scientists like Michael Faraday had shown that if you compress and cool a gas, you can force it into a liquid state. When that liquid is then allowed to evaporate, it absorbs heat from its surroundings, making them colder. It's the same principle your refrigerator uses. By doing this in stages, using one liquefied gas to cool and liquefy the next, more stubborn gas, they could cascade their way down the temperature scale. The great Scottish chemist James Dewar was a key figure in this race. Working at London's Royal Institution, he tackled the so-called permanent gases, like oxygen and nitrogen, that had resisted all previous attempts at liquefaction. The risks were huge. The combination of extreme pressures and cryogenic temperatures led to more than a few explosions in his lab. Dewar famously invented the vacuum flask, what we now call a dewar or thermos, to store these ultra-cold liquids. In 1898, he won a major prize in the race. He liquefied hydrogen, reaching the astonishingly low temperature of just 20 degrees above absolute zero. The world was stunned. They were closing in. But there was one gas left, a newly discovered element that was even more difficult: helium. The race to liquefy helium became the final frontier. Dewar's great rival, the Dutch physicist Heike Kamerlingh Onnes, was methodical and collaborative where Dewar was secretive and cantankerous. In 1908, Onnes and his team in Leiden finally did it. They liquefied helium, hitting a temperature of just 4 Kelvin, a mere 4 degrees above absolute zero. Onnes would win the Nobel Prize for this monumental achievement. They were at the doorstep of absolute zero. The classical dream of seeing the absolute death of motion seemed within reach. All they had to do was take those last few steps. But the universe, it turned out, had other plans. The journey into the unfathomable cold, reaching 4 Kelvin, was a landmark, but it was also where the real problems started. Scientists quickly discovered a frustrating truth. Getting cold is one thing, but getting colder is brutally hard. Each step closer to absolute zero took exponentially more effort. The reason why is in the nature of cooling itself. You're trying to remove energy from atoms. When there's a lot of energy, when the atoms are hot and moving wildly, it's relatively easy to siphon some of it off. But as the system gets colder and the atoms get more sluggish, there's just less and less energy left to remove. It's like trying to squeeze the last few drops of water from a sponge. This difficulty reflects a fundamental law of nature, another part of the third law of thermodynamics. It's impossible to reach absolute zero. You can get closer and closer, but you can never actually get there. It's an ultimate limit, just like the speed of light. For decades, progress stalled. The old methods had hit their limit. If we were going to get any closer to this forbidden temperature, we needed a new toolkit. That new toolkit arrived in the second half of the 20th century, and it came straight from the bizarre world of quantum mechanics. It was called laser cooling. The idea, first proposed in 1975, is both brilliant and deeply counterintuitive. How can you use lasers, beams of intense energy, to make something colder? The trick is to use the momentum of photons, the particles of light. Imagine an atom moving towards a laser beam. If the laser is tuned just right to a frequency slightly below what the atom naturally absorbs, the atom will only absorb a photon if it's moving towards the light. This is because of the Doppler effect, the same reason an ambulance siren sounds higher pitched as it comes toward you. For the atom moving toward the laser, the light's frequency gets shifted up, right into the sweet spot for absorption. When the atom absorbs the photon, it gets a tiny kick in the opposite direction, slowing it down. It then spits the photon back out in a random direction. Over millions of these cycles, the net effect is a consistent braking force. By setting up 6 intersecting lasers, scientists created what they poetically named optical molasses, a region of space where atoms get slowed down no matter which way they move. This technique, pioneered by scientists like Stephen Chu, Claude Cohen-Tannoudji, and William Phillips, who shared the 1997 Nobel Prize for it, was incredibly effective. It could cool a cloud of atoms down to millionths of a degree above absolute zero. But to get even colder, they needed another trick: evaporative cooling. First, a magnetic field is used to trap the laser-cooled atoms in a magneto-optical trap, or MO. Once the atoms are trapped in this magnetic bowl, the final, most brutal cooling stage begins. The scientists slowly lower the walls of the magnetic bowl. This allows the most energetic atoms, the hottest ones, to fly out and escape. As they leave, the average energy of the atoms left behind drops. It's the exact same reason your cup of coffee cools down. The hottest, fastest water molecules evaporate from the surface, leaving the cooler ones behind. By systematically kicking out the hottest atoms, scientists could force the temperature down into the nanokelvin range, billionths of a degree above absolute zero. This was a temperature colder than any known place in the natural universe. Deep space is a balmy 7 Kelvin, warmed by the afterglow of the Big Bang. These labs were creating temperatures billions of times colder. And it was here, in this realm of unimaginable cold, that quantum weirdness started to appear on a scale you could see. In 1995, two groups, one led by Eric Cornell and Carl Wieman in Colorado, and another by Wolfgang Ketterle at MIT, finally created something predicted 70 years earlier by Albert Einstein and Satyendra Nath Bose. They created a Bose-Einstein condensate, or BEC. This was a whole new state of matter. As the cloud of atoms got colder and slower, their quantum nature took over. According to quantum mechanics, particles like atoms also behave like waves. The colder an atom gets, the longer its wavelength becomes. In the extreme cold of the trap, the wavelengths of the individual atoms grew so large that they started to overlap. Then, at a critical temperature, something incredible happened. The atoms lost their individual identities and began to act as a single, coherent entity. The thousands of atoms in the trap had condensed into one giant, superatom, all described by a single wave function. It's not just that they were all in the same place. In a quantum sense, they had become the same thing. Creating the BEC was a triumph, earning a Nobel Prize in 2001. But it also presented a deeper mystery. The classical dream was to see atoms stop. In a BEC, the atoms are in their lowest possible energy state. They are as still as the laws of physics will allow. Yet, even here, a whisper away from absolute zero, the system was not perfectly motionless. There was a residual jiggle, an inherent tremor that simply refused to go away. The classical model was officially broken. The revelation. The quantum law of perpetual motion. So there was a profound problem. Scientists had built the most sophisticated refrigerators in history, pushing matter to the edge of absolute cold, only to find that their target perfect stillness was a mirage. No matter how much energy they removed, a tiny, residual motion remained. This wasn't leftover heat. This was something else. The answer didn't come from thermodynamics. It came from the strange, probabilistic world of quantum mechanics. And at its heart was Werner Heisenberg's uncertainty principle. The uncertainty principle is one of the most famous, and most misunderstood, ideas in physics. It's not a limit of our tools. It's a fundamental, built-in property of the universe. It states that you cannot simultaneously know with perfect accuracy both the position and the momentum of a particle. The more precisely you pin down a particle's position, the less precisely you can know its momentum, and vice versa. Think of it this way. To see a particle's position, you have to interact with it, maybe by bouncing a photon of light off of it. But that very act gives the particle a kick, changing its momentum in an unpredictable way. If you use a high-energy photon to get a really sharp position measurement, you give it a huge, random kick. If you use a low-energy photon to barely disturb its momentum, you get a very blurry picture of where it is. It's an inescapable trade-off. Now, let's apply this to the dream of absolute zero. The classical idea of absolute zero is perfect stillness. For an atom to be perfectly still, its velocity must be exactly zero. If its velocity is zero, its momentum is also exactly zero, with no uncertainty. But according to Heisenberg, if you know the momentum perfectly, then the uncertainty in the particle's position must become infinite. A particle with zero momentum would, in a sense, be everywhere in the universe at once. Its location would be completely undefined. Conversely, for an atom to exist in a specific spot locked in a crystal or held in a magnetic trap, its position isn't infinitely uncertain. It's confined. And because its position is at least partially known, its momentum cannot be perfectly known. It cannot be exactly zero. The particle must, by the fundamental laws of nature, be jiggling. It must be moving. This minimum, unavoidable energy of motion is called *0-point energy, ZPE*. It's the energy of the ground state, the lowest possible energy a system can have. In classical physics, the ground state energy is zero. In quantum mechanics, the ground state is a state of perpetual, irreducible vibration. This was the shocking revelation. The impossible motion scientists saw wasn't a flaw in their experiments. It was a direct, macroscopic manifestation of the Heisenberg uncertainty principle. It was the universe saying, you can get close, but you can never have perfect stillness, because that would violate my most fundamental rule. The idea of zero-point energy had been around since 1913, proposed by Einstein and Otto Stern, but for a long time, many treated it as just a mathematical quirk. But the race to absolute zero proved it was real. The persistent jiggle of atoms in Bose-Einstein condensates was concrete proof. One of the most dramatic examples is liquid helium. Helium is the only element that won't freeze under normal pressure, no matter how cold you make it. You can cool it all the way down to absolute zero, theoretically, and it will stay a liquid. Why? Zero-point energy. The helium atoms are very light and their bonds are very weak. The inherent quantum jiggle is strong enough to keep them from locking into a solid crystal. The atoms are simply too restless, too jittery from their quantum dance, to ever settle down and freeze. To force helium to solidify, you have to apply over 25 times normal atmospheric pressure just to cram the atoms together. So, the quest that began with a simple idea that cold is the absence of motion led to one of the most profound insights of modern physics. The universe, at its foundation, is not a quiet place. It's fundamentally and unceasingly restless. Proof and implications. The new reality. The idea of a perpetual quantum jiggle might sound like science fiction. For a long time, many physicists were skeptical. But over the past few decades, a series of brilliant experiments have not only confirmed its existence but have started to measure its effects, turning this ghost into a tangible feature of our reality. One of the most direct proofs comes from the very experiments trying to reach absolute zero. At the National Institute of Standards and Technology, NIST, researchers used atoms themselves as ultra-sensitive thermometers. They could see their supercooled atoms being affected by the faint thermal glow emitted by the walls of their vacuum chamber, even though the chamber itself was cryogenically cooled. This showed that even what we think of as an empty vacuum is teeming with energy that interacts with matter. The quest for cold continues to push boundaries. In a remarkable experiment in Germany, scientists used a 120-meter drop tower to achieve microgravity, allowing them to cool a beck of rubidium atoms to the coldest temperature ever recorded. Just 38 picokelvins, that's 38 trillionths of a degree above absolute zero. But even here, the atoms still possessed their fundamental zero-point energy, the minimum motion required by quantum law. Perhaps the most famous proof, though, comes from empty space itself. In 1948, the Dutch physicist Hendrik Casimir predicted something startling. He imagined two uncharged metal plates placed parallel to each other in a perfect vacuum. According to quantum theory, this empty vacuum is actually a roiling sea of virtual particles and fluctuating energy fields, the zero-point energy of space. All possible wavelengths of these energy fluctuations can exist outside the plates. But between the plates, only those wavelengths that fit perfectly into the tiny gap are allowed. This means there are more energy fluctuations pushing on the outside of the plates than on the inside. This imbalance, Casimir predicted, should create a tiny but measurable force, pushing the plates together. For decades, this Casimir effect was just a theory. But in 1997, it was finally measured, and the results matched the predictions perfectly. It was tangible proof that the vacuum of space is not empty. The zero-point energy of the quantum vacuum is real, and it exerts a physical force. The implications of this new reality are staggering. The classical notion of a quiet, static, empty void is gone. Even a perfect vacuum, stripped of all matter and cooled to absolute zero, is alive with energy. It redefines what nothing means. In the quantum sense, nothing is a state of minimum possible energy, not zero energy. And it tells us that absolute stillness is physically impossible. The universe is inherently restless. The dream of absolute zero wasn't a failure, it was a profound success. It didn't lead scientists to the destination they expected, but to a far stranger and more wondrous one. It was a journey that began seeking the end of motion, and ended by proving that motion can never end. The discovery of zero-point energy reveals a universe far stranger and more active than we ever imagined. It makes you wonder, if even the coldest, emptiest space is buzzing with hidden energy, what other fundamental secrets is the universe hiding from us in plain sight? What are your thoughts on this hidden world? Let me know in the comments below. And if you want to explore the mind-bending rules that make all of this possible, be sure to check out our next video on the quantum observer effect, and why reality itself might depend on the act of looking at it. The story of the impossible motion at absolute zero is one of the great intellectual journeys of modern science. It began with a simple, intuitive idea from the classical world. Temperature is motion, so if you remove all the heat, you'll get perfect stillness. This clear and compelling goal launched a century-long race to the bottom of the temperature scale, a saga of fierce rivalry and breathtaking ingenuity. From liquefying gases to trapping atoms with light, each generation got closer to 0 Kelvin, chasing the ultimate quiet at the heart of matter. But what they found at the frigid edge of reality was not silence. It was a hum, a persistent, unavoidable tremor. They discovered that the Heisenberg uncertainty principle forbids perfect stillness. To be perfectly still is to have a perfectly defined momentum, which would make an object's position infinitely uncertain a physical impossibility. The result is zero-point energy, a minimum, irreducible quantum jiggle that everything in the universe must have. It's the reason liquid helium refuses to freeze. It's the source of the Casimir force, a ghostly pressure that emerges from the empty vacuum of space. The heroic race to absolute zero didn't end with the discovery of perfect stillness. It ended with the revelation that motion is eternal. It proved that the universe isn't a static stage, but a fundamentally dynamic, vibrant, and ceaselessly restless entity. The quest to find the death of motion led us, instead, to discover the universe's eternal, unbreakable heartbeat. That faint, impossible hum is the fundamental music of the cosmos. The quantum glitch that forbids stillness. What's the coldest it can possibly get? For centuries, that question captivated scientists and philosophers. They imagined a journey down, past the frost on a winter morning, colder than any Arctic night, colder even than the dark, silent voids between the stars. Their destination was a final frontier of temperature, absolute zero. At -273.15 degrees Celsius, they believed that if you could just get rid of enough heat, you could achieve perfect, absolute stillness. A temperature so cold that every atom in the universe would freeze in its tracks, locked in a state of eternal silence. It was a beautiful, intuitive idea. Less heat means less motion. So, no heat must mean no motion. But when physicists finally got close, when they peered into the deepest chill imaginable, they didn't find the silence they were looking for. They didn't find perfect stillness. They found a glitch in the very laws of physics. A strange, stubborn rule of reality that forbids true stillness. They discovered that the universe can never, ever, truly stop moving. And this isn't just a technical problem, like not having a good enough freezer. This is a core feature of reality itself. The quest for ultimate cold didn't lead to an endpoint. It led to one of the most bizarre and profound discoveries in all of science. That even in the coldest, emptiest corners of existence, there is a frantic, unending dance. The quest for cold, the classical dream. To understand just how radical this discovery was, you have to appreciate the dream it replaced. Our story starts long before anyone had heard of quantum mechanics, back in the 17th and 18th centuries, a time of steam, gears, and a new confidence in the power of reason and measurement. This was the age of classical physics, a worldview where the universe ran like a giant, predictable clock. If you just knew the rules, you could predict anything. Scientists back then were fascinated by gases. They were invisible, seemingly weightless, but they had properties you could measure. One of the pioneers was a French scientist named Guillaume Amontons. Around 1702, using a pretty crude air thermometer, he noticed something fascinating. As he cooled a fixed volume of air, the pressure it exerted went down. Heat it up, pressure went up. And this relationship was strikingly consistent. It was predictable. Amontons figured that if cooling the air reduced its pressure, there must be some theoretical point of ultimate cold where the air would lose all its pressure entirely. His estimate was around -240 degrees Celsius, a stunningly close guess for the time, which we now know as -273.15 degrees Celsius. This idea laid the groundwork for one of the most important laws in gas physics. Nearly a century later, another French scientist, Jacques Charles, famous for his work with hot air balloons, refined the concept. In the 1780s, Charles ran a series of elegant experiments. Picture a piston in a cylinder with some gas trapped inside. Charles found that if you gently heat the gas while letting the piston move freely to keep the pressure the same, the volume of the gas expands. Cool it down, and the volume shrinks. And just like Amontons found with pressure, the relationship between temperature and volume was a perfect straight line. For every degree Celsius you dropped the temperature, the volume of the gas shrank by a fixed, predictable amount. This is where absolute zero went from a neat idea to a mathematical certainty. If you plot this on a graph, temperature on the horizontal axis, volume on the vertical, you get a straight line sloping down. You take your measurements at different temperatures, draw a line through them, and then you just extend the line. You ask a simple question. At what temperature does this line hit zero volume? Now, a real gas can't have zero volume. The atoms themselves take up space. Long before you'd get there, any real gas would turn into a liquid and then freeze solid. But here's the beautiful part. It didn't matter what gas you used. Oxygen, nitrogen, hydrogen, when you drew the lines for all of them, they all pointed to the exact same spot. That spot, the theoretical temperature where a perfect gas would shrink to nothing, was -273.15 degrees Celsius. This wasn't just some random number. It looked like a fundamental limit baked into the universe. You can't have negative volume, so you couldn't have a temperature colder than this. This insight led the brilliant physicist William Thomson, later known as Lord Kelvin, to propose a new temperature scale in 1848. Instead of putting zero at the freezing point of water, like Celsius, the Kelvin scale puts its zero at this ultimate, theoretical limit. So, Kelvin is absolute zero. Water freezes at a much less tidy 273.15 K. This scale was absolute because it wasn't based on some random substance like water, but on a fundamental property of energy itself. The idea was cemented by the laws of thermodynamics, the new science of heat and energy. The third law of thermodynamics later added a new twist. It says that as you get closer to absolute zero, the entropy, or disorder, of a system approaches a minimum. For a perfect crystal, that minimum is zero. But this law came with a frustrating catch. It's impossible for any process to reach absolute zero in a finite number of steps. Think of it like trying to walk to a wall by only taking steps that cover half the remaining distance. You get closer and closer, but you never actually touch it. Cooling something down works the same way. To cool something, you need to connect it to something even colder. To get to absolute zero, you'd need a reservoir that's already at absolute zero, which is a catch-22. Each step you take removes a smaller and smaller fraction of the remaining heat. Reaching the final 0K would take an infinite number of steps, which is physically impossible. So, by the end of the 19th century, the picture looked complete. Absolute zero was the universe's ground floor, a state of perfect order and, theoretically, perfect stillness. And while you could never quite get there, you could get tantalizingly close. Scientists imagined atoms slowing their frantic dance to a gentle sway, and finally, at the limit, coming to a perfect, silent rest. It was a clean, logical, and deeply satisfying picture. It was also completely wrong. The but moment. The turn to the quantum. The race to absolute zero became one of the great adventures of physics. Labs around the world competed to shave off the last fractions of a degree. They liquefied hydrogen, then helium, pushing temperatures down to just a few kelvins. The Dutch physicist Heike Kamerlingh-Onnes, a master of cold, got down to about 1.5 K in 1908, an achievement that would win him a Nobel Prize. With every new record, physicists expected to see the world of atoms slowing down, quieting down, and settling toward that final, dreamlike state of stillness. But as they pushed deeper into this realm of extreme cold, things started getting weird. The universe, it turns out, had a surprise waiting. The rules didn't just bend at these temperatures, they broke. While studying mercury at just 4.2 Kelvin, the boiling point of liquid helium, the coldest stuff he could make, Onnes discovered that its electrical resistance suddenly vanished. Completely. It had become a superconductor, able to carry a current forever with no energy loss. Classical physics had no clue why this would happen. Then came another puzzle, also with helium. Cool helium gas, and it turns into a liquid, as you'd expect. But cool it even further, below about 2.17 K, and it transforms again, into a state called a superfluid. This was a liquid unlike anything ever seen. It had zero viscosity, meaning it could flow without any friction at all. It could climb up the walls of its container and crawl out, seemingly defying gravity. It could squeeze through microscopic cracks that would stop any normal liquid. This was not the behavior of atoms quietly settling down. This was something active, coordinated, and deeply strange. Superconductivity and superfluidity were the first big cracks in the classical dream of a frozen, static world at absolute zero. They were visible signs of a hidden reality, the world of quantum mechanics. And this new reality had a completely different idea about what happens at the bottom of the temperature scale. The whole classical dream rested on one assumption: that you could, in principle, bring an atom to a complete stop. After all, temperature is just a measure of the average energy of motion. So, zero temperature should mean zero motion. But what if that was just wrong? What if the universe has a hidden rule that makes perfect stillness impossible? This is the great, but, moment in our story. As physicists looked closer, they realized that even at temperatures almost unimaginably close to absolute zero, a few billionths of a Kelvin, the atoms weren't still. They were still vibrating. There was a faint, irreducible tremor, a hum of energy that refused to be silenced, no matter how much heat they removed. This wasn't an error. It was a message from the universe itself. The goal physicists had been chasing for centuries, perfect stillness, wasn't just unreachable, it was a mirage. The universe forbids it. And the reason for this cosmic rule isn't found in thermodynamics. It's a quantum glitch, a fundamental feature of reality known as the Heisenberg uncertainty principle. The why? Unpacking the glitch Part 1. Heisenberg's ghost. In the early 20th century, while guys like Kamerlingh Onnes were exploring the weird world of extreme cold, another group of physicists was busy tearing down the old rules of reality. They were building quantum mechanics, and they were finding that the subatomic world was nothing like the predictable clockwork of Newton. One of the chief architects of this new, fuzzy reality was a young German physicist named Werner Heisenberg. In 1927, Heisenberg unveiled an idea that shattered the classical dream of a perfectly knowable universe: the uncertainty principle. It's often explained as a measurement problem that our clumsy tools disturb the thing we're trying to measure. While that can be true, the real principle is far deeper. It's not about the limits of our gear, it's a fundamental limit built into reality itself. The principle says there are pairs of properties, like a particle's position and its momentum, its mass times its velocity, that you can never know perfectly at the same time. There's an inherent fuzziness to the universe. The more precisely you pin down a particle's position, the less you can know about its momentum, and vice versa. Think of it like taking a photo of a speeding race car. If you use a super fast shutter speed, you freeze the motion and get a sharp, clear image. You know its position at that instant with great certainty. But that frozen image tells you almost nothing about its momentum. Was it speeding up? Slowing down? You just have a snapshot. High certainty of position, high uncertainty of momentum. Now, try a long exposure. You leave the shutter open as the car zooms by. The photo is a long, blurry streak. This blur tells you a lot about the car's momentum. The direction and speed are obvious. But where was the car at any single moment? It was everywhere along that streak. You have high certainty of momentum, but high uncertainty of position. The Heisenberg uncertainty principle is the universe's version of this trade-off. It's not just that it's hard to measure both, it's that a particle literally doesn't have a perfectly defined position and momentum at the same time. It exists in a cloud of probabilities. So, what does this have to do with absolute zero? Everything. Let's go back to that classical dream. At absolute zero, an atom would be perfectly still. If it's perfectly still, its momentum is exactly zero. Not close to zero, but precisely zero. We would know its momentum with absolute certainty. But what does Heisenberg's principle say is the consequence of that? If your uncertainty in momentum is zero, then your uncertainty in position must be infinite. An atom at absolute zero, if it were perfectly still, would have a perfectly known momentum, and therefore a completely unknown position. It could be literally anywhere in the universe. Which, of course, is ridiculous. If you've cooled a crystal in a lab, you know the atoms are in the crystal, in the lab. So let's flip it. Let's say we know the atom's position pretty well. In a solid crystal, an atom is locked into a lattice. It's confined to a very small area. So its uncertainty in position is very small. Now what does the uncertainty principle demand? If its position uncertainty is small, its momentum uncertainty must be large to keep their trade-off in balance. This is the heart of the quantum glitch. If an atom is confined in space, there must be some uncertainty in its momentum. Its momentum cannot be precisely zero. And if its momentum isn't precisely zero, it can't be perfectly still. It has to be jiggling. It has to be in motion. This isn't a choice, it's a non-negotiable law of quantum physics. An atom trapped in a crystal is like a firefly in a jar. We know it's in the jar, so its position is confined. But because it's confined, it cannot be still. It has to flutter. The very act of confining it guarantees its motion. This unavoidable, residual jiggle, mandated by the uncertainty principle, is the source of that mysterious hum physicists found at the edge of absolute zero. The universe, it seems, has a deep, constitutional objection to standing still. The why? Unpacking the glitch Part 2. Zero-point energy. Heisenberg's principle is the law, and the consequence of that law has a name. Zero-point energy. It's one of the most mind-bending concepts in physics, and it's the direct reason why stillness is forbidden. Zero-point energy, ZPE, is the lowest possible energy that a quantum system can have. In the old classical view, the lowest energy was zero, no motion, no heat, nothing. But quantum mechanics says that because of the uncertainty principle, a particle can never have zero kinetic energy. It must always have a minimum, non-zero amount of jiggle. This minimum energy is its ground state energy, or the zero-point energy. It's called zero point because it's the energy that remains at 0 Kelvin. You can't remove it from a system because it's not heat. It's a fundamental, structural part of the system itself, the energy of its own existence. Think of a guitar string. You can pluck it to make a loud sound. That's a high energy state. As the sound fades, the vibrations get smaller. You can even grab the string to stop it. To a classical eye, the string is now still, with zero energy. But in the quantum world, that's not true. The string is still pulled taut between 2 points. This state of tension is its ground state. It has potential energy just by being a string ready to be plucked. The only way to remove that energy would be to cut the string to destroy the system. Every particle in the universe is like that guitar string. It's confined in some way, an electron in an atom in a molecule. And because it's in a quantum box, it has a ground state energy greater than zero. This energy shows up as a constant, inescapable jiggle that persists even at absolute zero. And this isn't just theory. We see the effects of zero-point energy everywhere. The most dramatic example is helium-4. Under normal atmospheric pressure, every other substance in the universe will freeze solid if you cool it enough. But not helium. Helium remains a liquid, even at absolute zero. Why? Its atoms are very light and only weakly attracted to each other. Their zero-point energy, the amount of jiggling the uncertainty principle forces them to have, is actually greater than the energy of the bonds that would lock them into a solid crystal. The atoms literally jiggle themselves apart, refusing to freeze. This energy is also what keeps atoms from collapsing. In the old model, an orbiting electron should radiate away its energy and spiral into the nucleus in a flash. The reason it doesn't is because the electron is in a confined quantum state. Its lowest energy level, its zero-point energy, is in a stable orbital, not at the center. Without ZPE, matter as we know it couldn't exist. So the quest to find perfect stillness led to an incredible revelation. The quiet, frozen landscape scientists expected at absolute zero is a fiction. The reality is a world buzzing with a fundamental energy. The universe isn't a silent stage. It's a place with a constant background hum, a quantum vibration woven into the fabric of space itself. We just went from the classical dream of perfect stillness to the bizarre quantum rule that forbids it, and discovered an invisible energy that holds up all of reality. It's a fundamental glitch that makes our universe endlessly dynamic. If this kind of cosmic weirdness is your thing, and you want to keep exploring the glitches and secrets of the cosmos with us, hit that subscribe button and ring the bell so you don't miss our next trip into the weird. Your support helps us tackle these huge ideas. Now, let's look at what a universe without stillness really means. The implications. A universe that never sleeps. So, the universe has a permanent, unremovable hum. Stillness is forbidden. What does that actually mean for? Well, everything. It turns out the implications of zero-point energy stretch from the bizarre behavior of helium all the way to the largest scales of the cosmos, and they force us to completely redefine nothing. For most of history, a vacuum was the definition of nothing. True emptiness. A void. But quantum field theory says something astonishing. The vacuum is not empty. It's not nothing. The vacuum is simply the lowest energy state, the ground state of the fundamental fields that fill the universe. And just like a particle in a box, these fields have a zero-point energy. This means empty space is actually a seething, frothing cauldron of energy. This vacuum energy causes quantum fluctuations. For incredibly brief moments, pairs of virtual particles can borrow energy from the vacuum, pop into existence, and then annihilate each other, paying the energy back. This happens everywhere, all the time. The emptiest void in space is, at its most fundamental level, a chaotic frenzy. This sounds like science fiction, but there's proof. The most famous is the Casimir effect, predicted in 1948 by Dutch physicist Hendrik Casimir. Imagine you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a perfect vacuum. Classically, nothing should happen. But that's not what happens. Casimir realized that the space between the plates is different from the space outside. Outside, virtual particles of all wavelengths can pop into existence. But inside the tiny gap, only virtual particles with wavelengths that fit neatly into that gap are allowed. This means there are more virtual particles pushing on the outside of the plates than on the inside. The result is a tiny but measurable pressure pushing the plates together. This force has been measured. It is direct proof that the pressure of nothing is real, and it's a direct consequence of zero-point energy. The implications get even bigger when we look at the cosmos. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe isn't slowing down due to gravity, as everyone expected. It's accelerating. Some mysterious force is pushing space itself apart. They named this force dark energy. What is dark energy? We're still not sure, but the leading suspect is the energy of the vacuum itself, the zero-point energy of all the quantum fields in the universe. According to Einstein's theory of general relativity, energy has a gravitational effect. This means the ZPE of the vacuum should act like a kind of anti-gravity, pushing space to expand. But here's where we hit one of the biggest mysteries in all of science. When theorists try to calculate how much zero-point energy there should be in the vacuum, they get a number that is outrageously, catastrophically huge. It's 10 to the power of 120 times larger than the amount of dark energy we actually see. That has been called the worst theoretical prediction in the history of physics. If the vacuum energy were really that strong, the universe would have blown itself apart in the first split second of its existence. This massive discrepancy, known as the cosmological constant problem, tells us that while we know ZPE is real, our understanding of how it connects to gravity is profoundly wrong. Something is canceling out almost all of that immense energy, leaving just a tiny residue that is gently pushing our universe apart. So this quantum glitch that forbids stillness on the small scale reaches all the way up to the ultimate fate of the universe. It redefines emptiness, it pushes metal plates together, and it may be the engine behind the accelerating cosmos. The universe never truly sleeps. From the jiggle of an atom to the expansion of space, there is a restless energy that connects everything. We started with a simple question. What's the coldest it can get? We followed scientists who chased a dream of perfect stillness, a point called absolute zero where all motion was supposed to stop. They thought that at the bottom of reality, they would find silence. What they found instead was a glitch. A fundamental rule woven into the fabric of reality that says no. A law, born from the strange logic of the quantum world, that forbids perfect stillness. This glitch is the Heisenberg uncertainty principle, and its consequence is zero-point energy, an irreducible, unremovable hum of motion that animates every particle in the universe. This isn't a bug. It's a feature. It's why liquid helium refuses to freeze, why atoms don't collapse, and why the vacuum of space is a boiling sea of virtual particles. This quantum restlessness is the universe's heartbeat, and it can never be stopped. The quest for absolute zero didn't end in failure. It led to a revelation far more profound than the original goal. It taught us that the universe is not a static stage for events to unfold on, but is itself a relentless, vibrant, quantum dance. We live in a universe that, by its very nature, can never be truly still. So, what do you think? What does it mean to you that even in the deepest cold and the emptiest space, the universe is permanently, fundamentally, alive with motion? Let us know your thoughts in the comments. Physics' ultimate roadblock, the law that forbids stillness. Look closely at the world around you. A book resting on a table. A shard of ice, suspended in a frozen waterfall. A distant star, hanging like a diamond on black velvet. Our intuition tells us that stillness is the natural state of rest. It's the default. The end of the line. But what if I told you that's all a profound illusion? A cosmic lie we've accepted because our senses just aren't sharp enough to see the truth. What if there's a fundamental law of physics, more absolute than any freezer, that declares true stillness is utterly and completely forbidden? In the great rulebook of the universe, there's an ultimate roadblock, a law that ensures every single atom, from the core of our planet to the farthest reaches of space, is locked in an endless, invisible dance. Nothing ever stops. Today, we're taking a journey to the very bottom of temperature, to the mythical point of absolute zero, to understand why. We'll uncover not one, but two fundamental laws that slam the door on total stillness. One is a law of thermodynamics that makes the destination impossible to reach. The other is a law of quantum mechanics that says even if you could get there, everything would still be moving. This is the story of physics' ultimate roadblock, the law that forbids stillness. Imagine a single atom. To make it truly still, you'd have to do two things. First, stop its movement through space, pinning it to a single point. Second, stop all its internal motion, all its jiggling and vibrating. Our common sense says this should be simple. Just make it cold. Incredibly, profoundly cold. But as we follow this idea to its logical conclusion, we don't find simplicity. We find an infinite staircase leading to an impossible destination, guarded by the strange and ghostly rules of the quantum world. The quest for stillness isn't a simple matter of cooling. It's a battle against the very fabric of reality. The common sense of stillness, and why it's wrong. Our journey starts with a principle so basic it's often the first thing we learn in physics. Isaac Newton's first law of motion. An object at rest stays at rest. Seems obvious, right? A coffee mug on your desk is at rest. It's still. It's not moving. Case closed. Well, from our big, macroscopic point of view, yes. But physics is a story of shifting perspectives, of zooming in until the world we know dissolves into something far stranger. So, let's take that seemingly still coffee mug and put it under a hypothetical microscope with impossible power. As we zoom in, the smooth ceramic surface resolves into a complex, crystalline lattice of molecules. We push the magnification further, past the molecules, to the individual atoms that make them up. And here, our comfortable idea of stillness shatters completely. What we see isn't a serene, motionless grid. We see a world of furious activity. The atoms are vibrating, jiggling, and shaking in place like they're caught in a microscopic earthquake. They're bound together, sure, but they are far from still. This frantic dance is what we perceive, on our scale, as heat. Heat isn't some mysterious fluid that flows in and out of things. Heat is motion. Specifically, it's the kinetic energy of countless particles. When you touch a hot stove, that sensation of heat is just rapidly vibrating iron atoms transferring their energetic jiggling to the atoms in your fingertips, making them jiggle faster. And when you touch an ice cube, the feeling of cold is your own, more energetic atoms transferring their motion to the slower jiggling atoms of the ice, which causes your atoms to slow down. So, hot means fast, chaotic motion. Cold means slower, more subdued motion. This simple, powerful idea gives us a clear path to achieving true, absolute stillness. If heat is motion, then to stop all motion, we just have to remove all the heat. Every last scrap of it. This leads us to a concept that haunted 19th century scientists. A theoretical point of ultimate cold. A temperature so low that all this atomic vibration would just stop. A point where the universe would finally, truly, hold its breath. They called it absolute zero. On the temperature scales we use every day, it's a mind-numbingly cold destination. Minus 273, 15 degrees Celsius, or minus 459, 67 degrees Fahrenheit. On the scale designed for this very purpose, the Kelvin scale, it's the starting line. It is 0 Kelvin, the theoretical ground floor of temperature, below which you just can't go. The challenge, then, seems straightforward, even if it was technologically insane. To get perfect stillness, all we need to do is build a freezer powerful enough to reach 0 Kelvin. So, humanity set out on a multi-generational quest, a race to the bottom of temperature, believing that at the finish line, they'd find a world frozen in perfect silence. But what they found instead was a universe that refused to play along. They discovered that the closer you get to this ultimate cold, the harder the universe pushes back. They were about to run headfirst into a fundamental law of nature, a cosmic roadblock that makes the last step of the journey impossible. The question was no longer, how do we get there? But, why won't the universe let us arrive? The quest for absolute zero. A race to the bottom. The story of the quest for absolute zero is a scientific drama full of rivalry, brilliant innovation, and the relentless chase of an invisible goal. It all kicked off in the 19th century when physics giants like Lord Kelvin were figuring out the very nature of heat. The idea of an ultimate cold was no longer just a philosophical curiosity. It was a concrete target, a new South Pole for science to conquer. The first legs of the journey were about taming the so-called permanent gases, like oxygen and nitrogen, that had resisted all early attempts to turn them into liquids. The strategy was basically a cascade of cooling. Scientists like Raoul Pictet and Louis Cailletet developed techniques to liquefy one gas, then use that super-cold liquid to chill another, more stubborn gas to its own liquefaction point. It was a dangerous, high-pressure business. In 1877, they finally managed to create the first droplets of liquid oxygen, a pale blue liquid boiling at a frosty 90 Kelvin. Soon after, liquid nitrogen followed, at 77 Kelvin. One by one, the gases were falling. But one champion remained. Helium, the lightest and most elusive of them all. The race to liquefy helium became the defining challenge of low-temperature physics. A leading contender was the British chemist James Dewar, a master of cryogenics who invented the vacuum flask, the Dewar flask, which is the direct ancestor of our modern thermos. He'd successfully liquefied hydrogen in 1898, reaching an astonishing 20 Kelvin. But helium, predicted to boil below 5 Kelvin, was still out of his reach. The prize would ultimately go to the Dutch physicist Heike Kamerlingh Onnes. In 1908, after years of painstaking work, Onnes and his team used a combination of high pressure and the cooling effect of expanding gas to finally conquer helium. In a darkened room, they watched as the first glistening droplets of liquid helium formed, at a temperature of just 4.2 Kelvin. Humanity was now just 4 degrees away from absolute zero. The finish line seemed so close. With liquid helium as a new, ultra-cold starting point, the final assault on zero began. But this is where the race changed. It stopped being a sprint and became an agonizing crawl, with every fraction of a degree won through ever more complex and brilliant methods. The first technique was simple evaporative cooling. Just like blowing on hot soup helps the most energetic water molecules escape and cools it down, pumping a vacuum over liquid helium encourages the fastest helium atoms to evaporate, lowering the temperature of what's left. This could get them down to about 1 Kelvin. But to go further, they needed a new trick. That trick was called adiabatic demagnetization. It's a beautifully clever process that works by playing with the magnetism of atoms. Imagine a special kind of salt whose atoms behave like tiny, randomly oriented compass needles. First, you cool this salt as much as possible with liquid helium. Next, you hit it with a powerful magnetic field. This forces all those tiny atomic compass needles to snap into alignment. This act of creating order releases a little bit of heat, which gets carried away by the liquid helium. Then comes the crucial step. You thermally isolate the salt, cutting it off from everything else. Finally, you switch off the magnetic field. Freed from the magnet, the atomic compasses immediately randomize themselves. But to do this, to create that chaos, they need energy. And the only place to get that energy is by stealing it from the vibrations of the salt's own crystal structure. They suck the heat right out of themselves. The result? The salt becomes dramatically colder, plunging temperatures into the millikelvin range, thousandths of a degree above absolute zero. This method was the workhorse of low-temperature physics for decades. But even it had limits. To get to the truly infinitesimal temperatures microkelvin and nanokelvin, physicists in the late 20th century turned to a technology that sounds completely backward for cooling: lasers. Laser cooling doesn't work by simply chilling things. It works by stopping them. Imagine an atom moving through space. To slow it down, you need to give it a series of perfectly timed pushes in the opposite direction. That's what laser cooling does, using photons as the pushers. In a technique called Doppler cooling, scientists set up 6 laser beams pointing inwards from all directions, creating a kind of optical molasses. The lasers are tuned to a frequency just slightly below the frequency that the target atoms naturally absorb. Now, think about an atom moving towards one of those laser beams. Because of the Doppler effect, the same thing that makes an ambulance siren sound higher pitched as it comes toward you, the atom sees the incoming laser light as being shifted up in frequency. It gets shifted right into the atom's absorption sweet spot. The atom absorbs a photon, and that gives it a tiny kick, slowing it down. It's like the atom is running into a headwind made of light. After absorbing the photon, the atom spits it back out, but in a completely random direction. That emission gives the atom a kick too, but because the directions are random, those kicks all average out to zero over time. The net effect is a consistent slowing force from whatever laser the atom is moving towards. By surrounding the atoms with this optical molasses from all 6 directions, you can slow them down in every dimension, trapping them in a thick web of light and chilling them to temperatures of just millionths of a Kelvin. Using these techniques and their even more advanced successors, scientists have hit temperatures in the nanokelvin, billionths of a degree, and even picokelvin, trillionths of a degree, range. They've created bizarre new states of matter, like the Bose-Einstein condensate, where thousands of atoms cooled to a hair's breadth above absolute zero lose their individual identities and act like a single, giant superatom. This journey is one of the great epics of modern science. And yet, with all this staggering technology, with all this Nobel Prize-winning ingenuity, we have never reached zero. We can get to zero. 0.000000001K, but we can't take that final, tiny step. It's not a technological failure. Our freezers are good enough. The roadblock is something far more fundamental. It's a law woven into the very math of heat and disorder. To understand why the finish line is forever out of reach, we have to move past the engineering of cold and into the deep world of thermodynamics. We have to talk about entropy. The thermodynamic roadblock. Why the ladder has no final rung. With all this incredible tech, you'd be forgiven for thinking that reaching absolute zero is just a matter of more time and effort. If we can get to a billionth of a degree, surely we can close that final gap. But we can't. And the reason has to do with one of the most profound concepts in all of physics: entropy. Entropy was first dreamed up in the 19th century to understand steam engines. At its heart, it's a measure of how energy is spread out in a system. But over time, it's taken on a more intuitive definition. Entropy is a measure of disorder. Let's build an intuition for this. Imagine your bedroom. There is one, and only one, way for it to be perfectly tidy. Every book on the shelf, every shirt in the closet. This is a state of low disorder, low entropy. Now, think about a messy room. The books could be on the floor, on the bed, under the desk. The clothes could be on the chair, on the lamp, anywhere. There are millions of possible arrangements that all count as messy. This is a state of high disorder, high entropy. And as it turns out, nature loves a mess. There are simply more ways to be disordered than there are to be ordered. Here's another one. A deck of cards. Fresh out of the box, it's in a perfect, low-entropy state. Ace to king, sorted by suit. There's only one way for it to be in that state. Now, shuffle the deck. You've just increased its entropy. The cards are now disordered. And here's the kicker. There are a staggering number of possible shuffled arrangements, about 8 times 10 to the power of 67. If you tried to get back to that perfect, new deck order just by random shuffling, you'd be trying, on average, for longer than the age of the universe. This is the core of the second law of thermodynamics. In any isolated system, disorder either stays the same or it increases. A shuffled deck doesn't spontaneously unshuffle itself. So, what does this have to do with absolute zero? Remember, heat is the random motion of particles. A hot gas is a high-entropy system. The particles are flying around chaotically, their energy distributed in a huge number of ways. Cooling that gas means slowing the particles down and forcing them into lower energy states. You are reducing their randomness. You are decreasing their entropy. Reaching absolute zero would be the ultimate act of creating order. It would be a state where all thermal motion has stopped. Every particle is in its lowest possible energy state. There would be no randomness, no jiggling, no chaos. It would be the physical equivalent of that perfectly ordered deck of cards. It would be a state of minimum possible entropy. This is where the chemist Walther Nernst enters the story. He figured out what came to be known as the third law of thermodynamics. The law states that as you approach absolute zero, a system's entropy approaches a constant minimum value. For a perfect crystal, that entropy value is exactly zero. At absolute zero, with all thermal vibration gone, there would be only one single way for the system to exist. Its entropy would be zero. And this brings us, at last, to the roadblock. The unattainability principle, which is another way of stating the third law. It is impossible for any process, no matter how clever, to reduce the temperature of a system to absolute zero in a finite number of steps. Why? Let's visualize it. Imagine cooling is like walking down a flight of stairs, where each step down is one cycle of your cooling machine. At high temperatures, the steps are huge. Removing some heat energy gives you a big drop in temperature. You go down fast. But as you get colder, the stairs start to change. They get shorter. Removing the same amount of heat now results in a much smaller drop in temperature. The steps get smaller and smaller and smaller. As you approach the ground floor absolute zero, the steps become infinitesimally small. To get from 1 Kelvin to 0, 1 Kelvin is hard. To get from 1 Kelvin to 1 Kelvin is monumentally harder. The ground floor stays in sight, but you are now taking microscopic, futile steps. The journey from any finite temperature to absolute zero requires an asterisk infinite number of steps. This isn't just a metaphor, it's a mathematical reality. Every cooling process we have works by exploiting some form of entropy. You find a property of your system that can be ordered and disordered. Like those magnetic spins in the salt, you use a field to create order. Decreasing entropy and releasing heat, you dump that heat somewhere else, and then you release the field to let the system get disordered again, increasing its entropy by absorbing heat from itself. The third law says that the very handle you are using to cool the difference in entropy you can create vanishes as you get to the finish line. You're trying to empty a swimming pool with a bucket that shrinks to the size of a thimble, then an atom, then to nothing at all, the closer you get to emptying it. To cool something to absolute zero, you would need a cold reservoir that is already at absolute zero to dump your last bits of heat into. It's a cosmic catch-22. You need a piece of absolute zero to make a piece of absolute zero. So, the first roadblock is absolute. The third law of thermodynamics transforms the quest for absolute zero from a tech challenge into a logical impossibility. It's a destination you can get closer and closer to, but can never actually reach. But this is where the story gets even stranger. Even if we could somehow cheat, even if a wizard popped in and, with a wave of a wand, instantly teleported an atom to absolute zero, it still wouldn't be still. Because there's another, deeper, and far weirder law waiting for us. A law that says stillness itself is a violation of the quantum rules. The quantum jitter. The deeper, weirder roadblock. Let's just pretend for a second. We've broken the third law of thermodynamics. We have one atom, and we've magically removed every last bit of its thermal energy. It is officially at absolute zero. It should be perfectly, flawlessly still. But it isn't. It's still trembling. It's vibrating with a faint, ghostly energy that can't be removed, because this energy isn't heat. It's a fundamental property of existence. Welcome to the weird world of quantum mechanics, and our second, even more formidable roadblock. The Heisenberg uncertainty principle. Formulated by Werner Heisenberg in 1927, the uncertainty principle is a cornerstone of quantum theory. It's often explained by saying that the act of observing a particle changes it. To see an electron, you have to hit it with a photon of light. That photon bounces off the electron to your detector, but the impact is enough to knock the tiny electron off course. So measuring its position precisely makes its momentum uncertain. That analogy is helpful, but it doesn't capture the true, mind-bending reality. The uncertainty isn't because our measurements are clumsy. It's a fundamental, built-in feature of the universe. A particle doesn't have a perfectly definite position and a perfectly definite momentum at the same time. The principle is expressed in a famous little equation. Delta x, delta p, GeQ, h bar, 2. Delta x is the uncertainty in a particle's position. Delta p is the uncertainty in its momentum. And h bar is a ridiculously tiny but non-zero number. The equation says that the product of these two uncertainties can never be smaller than that tiny number. It can never be zero. This means you have a choice. You can know a particle's position with incredible precision, making delta x tiny, but if you do, its momentum becomes wildly uncertain. Delta p must get very large. Or, you can know its momentum with precision, making delta p tiny, but then its position becomes a complete mystery. Delta x gets huge. It's a cosmic seesaw. When one side goes down, the other must go up. So, what on earth does this have to with our atom at absolute zero? Let's define what perfectly still really means in physics terms. Perfectly still means two things. First, the particle isn't moving. Its velocity is exactly zero, which means its momentum is also exactly zero. If its momentum is perfectly zero, the uncertainty in its momentum, delta p, is also zero. Second, perfectly still implies the particle is asterisk at a specific location. It is pinned to a single point. This means we know its position with perfect certainty. The uncertainty in its position, delta x, would also have to be zero. So, for an atom to be truly still, both delta x and delta p would have to be zero. Their product would be zero. But the universe, via Heisenberg, says no. The product of those two uncertainties can never be zero. Let's follow the logic. If we say our atom is perfectly still, we're claiming its momentum is exactly zero, so delta p equals O. What does the uncertainty principle demand of its position? To keep the product from being zero, the uncertainty in its position, delta x, would have to become infinite. Think about what that means. An atom that is perfectly still would have no definite location. It would be smeared out across the entire universe. It would be everywhere at once. This is, to put it mildly, a physical absurdity. Therefore, the only way for a particle to asterisk exist at a location to be an atom in a crystal, or even just an atom in a trap, is for it to have some non-zero uncertainty in its position. And if its position uncertainty isn't infinite, then its momentum uncertainty cannot be zero. It must have some fuzziness in its momentum, which means its momentum can't be precisely, exactly zero. It must always have some leftover motion. This irreducible, minimum possible energy that a quantum system can have is known as its zero-point energy. It's a quantum jitter, a ceaseless tremor woven into the fabric of reality. You can think of it as a kind of quantum caffeine buzz that never, ever wears off. It's the universe's background hum. It's the energy a particle has just by existing. It's not thermal energy. You can't remove it by cooling, because it has nothing to do with temperature. It's a direct consequence of being a quantum object confined to a space. The particle pays an energy tax for having an address. This isn't just theory. Zero-point energy is real and has measurable effects. It's the reason liquid helium, even when cooled to the brink of absolute zero, refuses to freeze into a solid unless you put it under immense pressure. The zero-point energy of its atoms is so large that it overcomes the weak forces between them, preventing them from locking into a crystal. The helium atoms are literally too jittery to freeze. Even in what we think of as a perfect vacuum, empty space itself is seething with zero-point energy, with so-called virtual particles constantly popping into and out of existence in a roiling quantum foam. So the quantum roadblock is, in many ways, even more profound than the thermodynamic one. The third law tells us we can't complete the journey to absolute zero. The uncertainty principle tells us that even if we could arrive, we wouldn't find the stillness we were looking for. The very act of placing a particle somewhere guarantees that it must be in motion. Stillness, at the quantum level, is not just out of reach, it's logically impossible. It's forbidden by the fundamental rules of the game. We started with a simple idea that stillness is the absence of motion, achieved by removing all heat. We chased this idea to its ultimate conclusion, a quest for the perfect calm of absolute zero. But at every turn, the universe pushed back, revealing that our common sense ideas are just shadows of a deeper reality. we've slammed into two ultimate roadblocks. First, the third law of thermodynamics. It shows us that the path to absolute zero is an infinite journey. Cooling gets exponentially harder the colder you get, because the very tool you're using to extract heat entropy vanishes at the finish line. Reaching 0 Kelvin would take an infinite number of steps, making it physically impossible. And second, hiding behind that already impossible barrier, is the quantum roadblock. The Heisenberg uncertainty principle. It says that to be perfectly still, a particle would have to be everywhere in the universe at once. This fundamental rule endows every particle with an irremovable baseline of energy, a quantum jitter, called zero-point energy that persists even at absolute zero. So, nothing is ever truly still. Not the ice in your glass, not the rock on the ground, not the atoms that make you. This isn't a flaw in the universe. It's a fundamental and beautiful feature of our reality. The universe isn't a static photograph. It's a dynamic, ceaselessly vibrating system, from the grand cosmic ballet of galaxies down to the frantic, invisible dance of a single atom. The next time you see something that looks perfectly calm, perfectly frozen, remember the secret it's hiding. Remember the ceaseless, microscopic rave happening within. A frantic, invisible dance that connects it to the fundamental, restless energy of the entire cosmos. Stillness is the illusion. Motion is the unshakable, ultimate reality. If this journey into the heart of physics blew your mind, consider subscribing and hitting the bell so you don't miss our next exploration into the weird and wonderful rules that govern our universe. And let us know in the comments, what other, impossible, concepts in physics should we tackle next? Creating a fifth state of matter with lasers. Imagine you could cool a cloud of atoms down so much that the very idea of an individual atom just dissolves. Imagine millions of them losing their identities and starting to move, vibrate, and act as one single, enormous, superatom. It sounds like something from a sci-fi novel, but it's real. In labs all over the world, scientists are doing just that. They're creating a state of matter that, for most of cosmic history, really shouldn't exist. They do it by blasting atoms with an intricate ballet of lasers, pushing them to temperatures a billionth of a degree above the coldest anything can possibly be. Absolute zero. It's a journey into a realm of physics so strange and counterintuitive, it forces us to question our most basic ideas of what it means to be matter. This quest to create the coldest spots in the universe reveals something profound. That everything, from you to the stars, is locked in a perpetual, unbreakable dance, a constant buzz of energy dictated by the beautiful and bizarre laws of the quantum world. Today, we're going to pull back the curtain on that dance. We're going to build a Bose-Einstein condensate. Let's start with an idea we all know. The basic states of matter. You have a solid, like ice. Add some heat, and it melts into a liquid. Add more energy, and it boils into a gas. Add a asterisk whole lot more, enough to rip electrons from their atoms, and you get a fourth state. Plasma, the stuff of stars. For centuries, that was the whole story. A one-way street where adding energy makes things more chaotic. But what happens if you go the other way? What if you start with a gas and begin pulling energy out? And I don't just mean cooling it down a little. I mean pulling out nearly all of it. What happens when you get as close as you possibly can to absolute zero, the theoretical point of zero energy? For a long time, the classical answer was simple. Everything would just stop. Every atom would freeze solid in its place, a perfect, silent crystal. It's a beautifully simple picture. And it's completely wrong. To understand why, we have to go back to the 1920s, when physics was being turned on its head. A fifth state on paper. In the early 1920s, the quantum revolution was in full swing. Physicists were grappling with the wild idea that particles like electrons weren't just tiny little balls, but also behaved like waves. In 1924, a brilliant but then unknown physicist from India named Satyendra Nath Bose was working on a problem with photons. He developed a new way to count them, a new statistic that treated them as truly indistinguishable. He wrote up his findings, but a major physics journal rejected the paper. So, Bose did something bold. He mailed his paper directly to the most famous scientist in the world, Albert Einstein. Einstein immediately saw the genius in Bose's work. He not only translated the paper into German and got it published, he took the idea one giant leap further. Einstein realized that this new way of counting these Bose statistics shouldn't just apply to light. It should also apply to certain types of atoms. He did the math. What would happen, he wondered, if you took a gas of these special atoms and cooled it down, way down? His calculations predicted something astonishing. As the atoms lost energy, they wouldn't just slow down and freeze. Instead, below a certain, incredibly low temperature, the atoms would undergo a phase transition unlike any other. They would stop their chaotic individual motions and all fall, at once, into the single lowest possible energy state available. It would be like a crowded room of people running around randomly, then suddenly and simultaneously deciding to sit in the exact same chair. They would lose their individual identities and behave as a single, coherent quantum entity. A new state of matter. This theoretical state was eventually named for its two visionaries, the Bose-Einstein condensate, or BEC. For decades, that's all it was. A ghost on a page, a mathematical curiosity. The temperatures were impossibly cold, far colder than deep space. No refrigerator in the universe, natural or man-made, could get close. The quest to actually see a BEC would require a whole new way of thinking about temperature and a new set of tools. The challenge was laid down, but it would take 70 years, and the invention of the laser, for humanity to finally answer it. The quantum weirdness you need to know. Before we build the world's most extreme refrigerator, we have to understand why it works. And this is where things get weird. The key to a BEC is letting go of the idea that an atom is just a tiny marble. It isn't. Thanks to wave-particle duality, every atom also has a wave-like nature. You can think of this as its quantum fuzziness. This wave is called the de Broglie wavelength, and its size is tied to the atom's momentum. A hot, energetic atom has a tiny wavelength. It acts like a little billiard ball. But as you cool it down, it loses momentum and its wavelength expands. The atom becomes less like a point and more like a broad ripple. Now for piece number 2. The universe divides particles into two families, fermions and bosons. Fermions are the ultimate individualists. The Pauli exclusion principle says no two identical fermions can ever be in the same quantum state. They refuse to share space, which is why electrons stack up in neat shells around an atom, giving us the entire periodic table. Bosons, on the other hand, are social butterflies. They love to clump together in the exact same quantum state. An unlimited number can occupy the same energy level, the same position, the same everything. The atoms we use to make a BEC, like rubidium-87, are bosons. And that's the secret ingredient. So, let's put it all together. You have a gas of these bosonic atoms. At room temperature, their wavelengths are tiny. As you cool them, their wavelengths grow. As you get colder and colder, these waves get so large they start to overlap. Because they're bosons, they're happy to merge. When you finally hit that critical temperature, something magical happens. The individual waves snap together into a single, massive matter wave. All the atoms fall into the lowest energy state, and their individual identities are gone. They have become one coherent whole. The superatom. The Bose-Einstein condensate. But what about that idea of everything stopping at absolute zero? That's foiled by one of quantum mechanics' most fundamental rules. The Heisenberg uncertainty principle. Simply put, you can't know both the exact position and the exact momentum of a particle. If an atom were perfectly still, zero momentum, its position would be infinitely uncertain. The universe forbids perfect stillness. Even at absolute zero, an atom must retain a minimum jiggle, its zero-point energy. In a Beck, all the atoms possess this same minimum energy. They jiggle, but they jiggle together, in perfect unison. The toolkit for absolute zero. Lasers and magnets. So, how do you actually reach temperatures just a few billionths of a degree above absolute zero? You can't use a normal fridge. The answer, brilliantly, is to use light. Which sounds like a paradox. How do you use lasers' beams of energy to make something colder? Part A. Laser cooling. The optical molasses. The first step is a revolutionary technique called laser cooling, which earned its creators the 1997 Nobel Prize in Physics. It works using two simple ideas. Light carries momentum, and the Doppler effect. We know light can push things. When an atom absorbs a photon, it gets a tiny kick. As for the Doppler effect, you hear it all the time with sound. An ambulance siren sounds higher as it comes toward you and lower as it goes away. The same thing happens with light. If an atom moves toward a laser, it sees the light as slightly higher in frequency, or blue shifted. If it moves away, it sees it as red shifted. Here's the trick. Atoms are picky. They only absorb photons of a very specific frequency. Scientists take a cloud of atoms and fire lasers at it from all 6 directions. But they tune the lasers to a frequency that's slightly lower than the atom's preference. Now, imagine an atom zipping to the right. As it moves toward the laser on the right, the Doppler effect makes that light appear perfectly tuned for absorption. So, it absorbs a photon. Wham! It gets a kick backward, slowing it down. Meanwhile, the laser on the left is now the wrong color, so the atom ignores it. This happens from all directions at once. No matter which way an atom moves, it's more likely to get a kick opposing its motion. It's as if the atom is wading through a pool of thick, invisible honey. This optical molasses creates a powerful friction force with light, dramatically slowing the atoms. In less than a second, this cools the gas to a few millionths of a degree above absolute zero. Fantastically cold, but still too hot for a Beck. Part B. The magnetic trap. A quantum prison. Laser cooling has a limit. To go deeper, we need to trap the atoms. This is done with a magneto-optical trap, or MO. This brilliant invention combines laser cooling with a magnetic field that is zero at the very center and gets stronger in every direction you move away. Now we add another quantum trick. The Zeeman effect. A magnetic field can slightly alter an atom's energy levels. In the MO, the field is set up so that atoms straying from the center become more likely to absorb the cooling laser light, pushing them back. The lasers are the molasses, slowing the atoms down, and the magnetic field provides the walls, nudging any escapees back to the middle. The result is a small, dense, glowing ball of up to 1 billion atoms, suspended in the vacuum as if by magic. We have our atoms trapped and pre-chilled. Now, for the final plunge. Part C. Evaporative cooling. The final plunge. To get past the limits of laser cooling, the scientists turn the lasers off. The glowing ball vanishes, but the atoms are still held by a purely magnetic trap that acts like a bowl. And now, the final, most intuitive cooling technique begins. Evaporative cooling. It's the exact same reason a cup of hot coffee cools down. The hottest, fastest water molecules escape as steam, taking their energy with them and lowering the average temperature of what's left. Physicists do the same with their trapped atoms. They use radio frequency fields to create a lip on their magnetic bowl. At first, only the very hottest atoms have enough energy to fly over the lip and escape. As they leave, the remaining cloud gets colder. Then, the physicists lower the lip a little more. Again, the new, hottest atoms escape. The remaining cloud gets colder still. They repeat this, methodically shaving off the most energetic atoms. With each step, the cloud gets smaller, denser, and its temperature plummets from millionths to billionths of a degree above absolute zero. They're now in the regime Einstein predicted. The de Broglie wavelengths are swelling and overlapping. With one final, careful lowering of the trap, they push the cloud over the edge. The phase transition happens. In the silent heart of a vacuum chamber, a Bose-Einstein condensate is born. The discovery: we got it. For 70 years, the Beck was pure theory. But in June 1995, at Gila in Colorado, that all changed. Physicists Eric Cornell and Carl Wieman had spent years assembling the complex machinery needed to make the final plunge. They ran the sequence, chilling a cloud of rubidium-87 atoms into the nanokelvin range. But how would you know if you had it? You can't just look at a few thousand invisible atoms. Their ingenious detection method relied on turning off the trap and watching what happened. A normal cold gas would expand uniformly, like a puff of smoke. But a Beck, as a single quantum wave, would behave differently. So, they switched off the magnetic trap, let the cloud expand for a moment, and took a shadow picture with a laser. They processed the data, expecting to see a broad hump representing a normal gas. What they saw was breathtaking. There was the broad hump of the remaining thermal atoms, but right in the middle was a sharp, dramatic spike. A tiny, incredibly dense peak of atoms that had barely expanded at all. That spike was the condensate. After 7 decades of theory, the discovery was quickly published, and humanity had officially created the fifth state of matter. The news electrified the physics community. A few months later, a team at MIT led by Wolfgang Ketterle not only confirmed the discovery with sodium atoms but created larger condensates and performed one of the most beautiful experiments in quantum physics. They made 2 separate BECs and let them expand into each other. Just like overlapping water waves, the 2 matter waves created a distinct interference pattern. It was unambiguous proof of the condensate's wave-like nature. For the achievement of Bose-Einstein condensation in dilute gases of alkali atoms, Cornell, Wieman, and Ketterle shared the 2001 Nobel Prize in Physics. The frontier. Why we build these things? Creating a new state of matter is amazing, but what can you do with it? Why do labs keep building these complex machines? The answer is that BECs are one of the most powerful tools we have for exploring the quantum world. A huge challenge has been that BECs are typically created in brief, fleeting pulses. But in work published in 2022, researchers at the University of Amsterdam achieved a major breakthrough: a continuous Bose-Einstein condensate. By cleverly creating a system that moves atoms through different cooling stages spatially, they could replenish the condensate with new ultracold atoms as fast as old ones were lost, allowing it to be maintained indefinitely. This transforms the Beck from a short-lived pulse into a continuous, steady stream, opening the door for a true, continuous wave atom laser. And this isn't the only frontier. In research announced in 2024, a team at Columbia University created a Beck out of molecules for the first time. This was a monumental challenge, as molecules are much more fragile than atoms. This opens up whole new fields, allowing scientists to study chemical reactions at ultracold temperatures with unprecedented control. Perhaps the most profound application is quantum simulation. By tweaking the lasers and magnets, scientists can program a Beck to mimic other, less accessible quantum systems like the environment around a black hole's event horizon. And because a Beck is a single coherent entity, it's exquisitely sensitive to its environment. This makes it the heart of atom interferometry, which uses matter waves to measure forces like gravity with astonishing precision. This could lead to hypersensitive navigation systems for planes or submarines that work perfectly without GPS. Of course, there's the connection to quantum computing. The collective state of a Beck is naturally robust against the environmental noise that plagues other quantum systems, making it a candidate for quantum memory. And finally, BECs might even help us solve one of the biggest mysteries in science: dark matter. Some theories predict that the vast clouds of hypothetical particles called axions could have formed a galaxy-sized Beck over billions of years. By studying BECs in the lab, we can learn what signatures to look for in the sky. From a speculative letter mailed to Einstein a century ago, the Bose-Einstein condensate has journeyed from a mathematical ghost to a tangible reality. It's a state of matter born from the strangest rules of quantum mechanics, a testament to what we can achieve when we push the boundaries of cold and control. Creating a Beck is more than a quest for a record low temperature. It's about opening a macroscopic window into the hidden quantum world, letting us see the wave nature of matter and the collective behavior that governs the universe. The journey to absolute zero reveals that there is no true stillness, only a perpetual quantum dance. And by learning the steps to that dance by choreographing atoms with lasers and magnets, we are not only building tools that will redefine technology, but we are also getting closer to understanding the very fabric of reality itself. The super atoms we create in these labs are whispering the secrets of the cosmos, and we are finally learning how to listen. If you enjoyed this deep dive into the quantum world, you might want to check out our video on quantum entanglement, one of the strangest predictions of quantum theory, where the reality is even weirder. And to join us for more explorations into the frontiers of science, make sure to subscribe and hit that notification bell. The impossible motion inside absolute zero. Imagine the coldest possible point of stillness. A temperature called absolute zero, where all the jiggling and vibrating of atoms should just stop. For centuries, we thought of this as the universe's ultimate off switch. A theoretical point, Kelvin, where you've squeezed out every last drop of thermal energy and atoms no longer tremble with heat. It was the final frontier of cold, a state of perfect, deadly silence where the chaotic dance of matter would finally end. But what if I told you that's not the whole truth? What if the very act of existing means a particle can never be truly still? The closer we look, the more we find a mysterious, impossible motion, a quantum jitter that can never be stopped. The reason why reveals one of the most bizarre and fundamental truths about our universe. A rule that says reality, at its most basic level, never really goes to sleep. The classical dream of absolute stillness. To really get how strange this is, we first have to understand the old dream it shattered. For most of history, hot and cold were just things we felt. The why was a total mystery. It wasn't until the 1800s that scientists landed on a revolutionary idea. Temperature isn't a thing, it's a asterisk motion. What we feel as heat is just the chaotic jiggling of countless atoms. A hot cup of coffee is a microscopic mosh pit of hyperactive water molecules, vibrating and slamming into each other billions of times a second. A cold glass of ice water? It's a much calmer scene. The molecules are still moving, but their dance is way more subdued. This simple idea that temperature is just the average energy of moving particles led to a logical question. If you make things colder by slowing their atoms down, what happens if you slow them down all the way? What happens when their kinetic energy hits zero? That question gave birth to the concept of absolute zero. Scientists like Lord Kelvin worked backward from how gases behave, calculating the theoretical temperature where all this particle motion would just stop. They landed on -273. 15 degrees Celsius, or 0 on the Kelvin scale, a scale designed with this ultimate endpoint in mind. The idea was a physicist's paradise. It promised a state of perfect order, a world stripped of messy, random heat. Imagine a crystal cooled to absolute zero. In this classical dream, every single atom would lock perfectly into place, motionless and silent. It represented zero entropy, the ultimate state of order. You could, in theory, know the precise location and precise momentum, which would be zero, of every single particle. It was a universe you could pause. This dream kicked off a century-long race to the bottom, a relentless quest to get colder and colder. Scientists developed brilliant new ways to refrigerate things. They turned gas after gas into liquid, first oxygen, then nitrogen, then hydrogen, each step getting them closer to that finish line. The final holdout was helium, which they finally liquefied at a frigid 4.2 Kelvin, just a few degrees from the goal. The path to absolute zero seemed clear. The destination was on the map. But as physicists tiptoed into this new realm of extreme cold, they found something deeply unsettling. The universe wasn't playing by their rules. The map was wrong, because the world it described, a world of perfect stillness, was a fantasy. The first cracks in the ice. A quantum roadblock. The early 20th century turned physics upside down. The neat, clockwork universe of Isaac Newton was being replaced by a strange, probabilistic, and frankly weird new reality: quantum mechanics. This new science showed that on the tiniest scales, the rules we take for granted just don't apply. It told us particles like electrons could also act like waves, existing not as tiny dots but as spread-out fields of probability. It told us energy came in chunky, discrete packets called quanta. Reality, at its core, was fuzzy. And it was from this new, strange world that the roadblock to absolute zero emerged. The person who delivered the news was a young German physicist named Werner Heisenberg. In 1927, he came up with one of the pillars of modern physics: the Heisenberg uncertainty principle. In simple terms, the principle makes a shocking claim. You can't simultaneously know both the exact position and the exact momentum of a particle. The more you pin down one, the fuzzier the other becomes. And this isn't because our tools are clumsy. It's a fundamental, baked-in feature of reality. Think of it like trying to take a picture of a race car. If you want to know its exact position, you use a super-fast shutter speed. Click. You get a crisp, clear photo of the car, frozen in one spot. You know its position perfectly. But you have no idea how fast it was going. Was it doing 100 or 200? You can't tell. To figure out its momentum, you'd need a longer shutter speed to capture a blur. Now, from the length and angle of that blur, you get a good sense of its speed and direction, but its exact position at any one moment is lost. You've traded certainty in position for certainty in momentum. The uncertainty principle is the universe's version of this trade-off. To see a tiny particle like an electron, you have to hit it with something, usually another particle like a photon of light. If you want to pinpoint the electron's position with incredible accuracy, you need to hit it with a high-energy photon. But when that high-energy photon smacks into the electron, it's like a cannonball hitting a marble. The collision sends the electron flying off in a new, unknown direction. So, in the very act of measuring its position, you've completely changed its momentum. You knew exactly where it was, but you have no idea where it's asterisk going. Okay, so what if you try to be gentle? To measure its momentum without disturbing it, you could use a very low-energy photon. This wouldn't kick the electron very hard. But a low-energy photon has a long wavelength, which is like trying to feel the shape of a tiny screw while wearing a giant oven mitt. The information it gives you about the electron's position is incredibly fuzzy. You'd know its momentum, but you'd have only a vague idea of where it is. But the deepest truth is even stranger. The uncertainty isn't just about measurement, it's about what a particle is. A particle is best described as a wave packet, a ripple of probability. To create a particle that exists in a specific location, you have to combine many different waves. Because this localized particle is made from a mix of waves, it no longer has one single, certain momentum, it has a range of possible momentums. So, a particle with a definite position is, by its very nature, a particle with an uncertain momentum. And vice versa. The two are locked in a cosmic trade-off. It's a fundamental law, and it's this law that stands guard at the gates of absolute zero, forbidding entry. The reveal. Zero-point energy. So now, let's connect the dots. On one hand, we have the classical dream of absolute zero, perfect stillness. On the other, we have Heisenberg's cosmic rule. You can't know position and momentum perfectly at the same time. The collision of these two ideas is where the impossible motion is born. Think about what perfectly still really means. It means a particle's momentum is exactly zero. Not close to it, but a perfect, mathematical zero. If its momentum is exactly zero, then our uncertainty about its momentum is also zero. We know it with absolute precision. This is where the uncertainty principle delivers the knockout punch. The principle states that the uncertainty in position, times the uncertainty in momentum, has to be more than a specific, tiny, non-zero number. So if you set the uncertainty in momentum to zero, the equation demands that the uncertainty in position must become infinite. Let that sink in for a second. A particle that is perfectly still would have to exist everywhere in the universe at the same time. It would have no specific location. It would basically be a ghost, smeared across the entire cosmos. The universe doesn't allow for that kind of nonsense. A particle has to be somewhere. Its location can't be infinitely uncertain. And if its uncertainty in position is finite, then the uncertainty principle demands that its uncertainty in momentum must be greater than zero. This leads to a mind-blowing conclusion. A particle can never have a momentum of exactly zero. Its momentum must always have some wiggle room. It has to constantly fluctuate, jiggling back and forth purely as a consequence of its own existence. It can get incredibly close to zero motion, but it can never truly reach it. This minimum, inescapable energy that a system must have, even at absolute zero, is called *0-point energy. It's the energy of the ground state. It's the price of admission for existing in a quantum universe. It's a fundamental tremor woven into the fabric of reality. Even in the coldest, darkest vacuum of space, at the lowest possible energy state, everything is humming with this faint, quantum jitter. This is the impossible motion. It's not a failure to reach absolute zero, it's a fundamental requirement of being a particle. A particle is only allowed to exist if it agrees to keep moving, just a little bit, forever. The dream of a perfectly frozen, silent universe is impossible. Absolute zero isn't an off switch. It's just the point where all thermal motion stops, leaving behind only this strange, ghostly, and absolutely necessary quantum motion. The implications. A universe that never sleeps. So, this impossible motion, this zero-point energy, is a fundamental rule. It's a mind-bending concept, but does this tiny jitter actually matter in the real world? Oh, yes. Zero-point energy isn't just a quirky footnote. It's responsible for some of the most bizarre phenomena we've ever seen. Let's start with the most direct proof. The liquid that refuses to freeze. Under normal atmospheric pressure, every substance, when you cool it down enough, will eventually turn solid. Every substance, that is, except one, helium. Cool it down, and it becomes a liquid at about 4.2 Kelvin. But then, you can keep cooling it. 3 Kelvin, 2 Kelvin, 1 Kelvin. All the way toward absolute zero, and it just stays liquid. The reason is zero-point energy. Helium atoms are extremely light, and the forces holding them together are incredibly weak. That mandatory quantum jitter is stronger than the feeble bonds that would normally lock the atoms into a solid crystal. The atoms are just too restless to settle down. While it can be forced to solidify under immense pressure, about 25 times what we experience at sea level at normal pressures, helium remains a liquid stirred only by its own unstoppable quantum motion. And the weirdness doesn't stop there. Cool liquid helium-4 below about 217 Kelvin, and it transforms into a baffling state of matter called a superfluid. A superfluid has zero internal friction. If you stir a cup of coffee, it stops spinning after a few seconds. If you could stir a cup of superfluid helium, it would theoretically spin forever. A superfluid seems to defy logic. It can crawl up and over the sides of a container, apparently ignoring gravity, as a super-thin film coats every available surface. It can flow through microscopic cracks that would stop any normal liquid, or even a gas. This is the quantum world invading our large-scale reality. As the helium atoms get colder, their wave-like natures overlap and they condense into a single, massive quantum state, acting like one giant, super atom. Their individual zero-point jitters become one coherent, collective motion, allowing for this bizarre, frictionless flow. We've even created this state of matter in the lab. The quest for cold has gotten us astonishingly close to absolute zero. Using lasers and magnetic traps, researchers have reached temperatures as low as 38 picokelvin, that's 38 trillionths of a degree above absolute zero. At these unimaginable temperatures, thousands of atoms can merge into a Bose-Einstein condensate, Beck, a speck of matter where thousands of atoms act in perfect unison, a quantum phenomenon you can see. The implications even stretch into empty space. According to quantum field theory, a vacuum isn't truly empty. It's a simmering soup of zero-point energy. This vacuum energy can be measured through effects like the Casimir effect, where two uncharged metal plates in a vacuum are pushed together by an imbalance of virtual particles that pop in and out of existence around them. This all comes together in our pursuit of quantum computing. To work, quantum computers have to be kept near absolute zero to protect their fragile states from thermal noise. But even there, they face fundamental limits. There's Landauer's principle, which says that erasing information must release a tiny amount of heat. And the qubits themselves, the heart of the computer, can never be brought to a complete stop because of their own zero-point energy. That inherent motion is a source of potential error engineers must constantly fight against. The dream of a perfect, silent computer runs into the same wall as the dream of a perfect, silent universe. The impossible motion. We started with a simple idea: a perfectly still universe at absolute zero. We saw it as the final, quiet end. But we found that this dream was shattered by the weird, wonderful rules of the quantum world. We met the Heisenberg uncertainty principle not as a limit on our tools, but as a non-negotiable law of reality. A cosmic trade-off that forbids perfect stillness and gives rise to zero-point energy, an impossible, unstoppable motion that every particle must have simply to exist. We saw how this quantum jitter isn't just theory. It keeps helium liquid in the deepest cold, orchestrates the ghostly dance of superfluids, and creates the bizarre collective state of a Bose-Einstein condensate. It's the energy of empty space and a fundamental challenge in our most advanced technology. So, the impossible motion inside absolute zero isn't a paradox. It's a revelation. It tells us that the universe, at its most fundamental level, is relentlessly active. The quest to reach absolute zero wasn't a failure. It led to the discovery of a deeper truth. A truth that says even in the most profound cold, the universe never truly sleeps. It is, and always will be, alive with the hum of quantum motion. Science just proved reality has no off switch. What if I told you there's an off switch for reality? A switch that could stop time, freeze motion, and bring the entire universe to a perfect, silent standstill. For over a century, some of the smartest people on the planet thought they knew how to find it. The plan was simple, elegant, and honestly, a little terrifying. Just make something really, really cold. I'm not talking about winter in Antarctica. Cold. We're talking about the coldest temperature possible. A point so fundamentally frigid that the frantic, chaotic dance of every atom in the universe would finally just stop. They even gave it a name: absolute zero. At this ultimate limit, -273, 15 degrees Celsius, everything was supposed to grind to a halt. It was the end of the line for energy, the ultimate state of stillness. If you could reach it, you could, in a very real sense, turn off a piece of reality. But it turns out, the universe has a secret, a loophole in the plan. A fundamental rule of the game that makes true stillness, true silence, completely and utterly impossible. Science has discovered that the universe doesn't have an off switch. Instead, it has a heartbeat. A constant, irreducible, and endless vibration that hums through every fiber of space-time. And by the end of this, you'll see that nothing, not you, not the world around you, not even empty space itself, is ever truly still. The classical dream of stillness. To get why reality has no off switch, we first have to understand the beautiful, and ultimately flawed, dream of the scientists who thought they could build one. It all started with a simple question: what is heat? For most of history, people thought it was some kind of invisible fluid called caloric that flowed from hot things to cold things. But in the 19th century, a handful of brilliant minds realized heat wasn't a thing at all. It was motion. Think of it like this. The air you're breathing right now is filled with trillions of nitrogen and oxygen molecules zipping around at hundreds of meters per second, smashing into each other billions of times every second. The warmth you feel from a cup of coffee is just the sensation of hyperactive water molecules transferring their frantic energy to your hands. Temperature, they realized, is just a measure of how fast particles are moving. Hot means fast. Cold means slow. This revelation immediately sparked a tantalizing idea. If you make things hotter by speeding atoms up, can you make something perfectly still by slowing them down? What happens if you just keep pulling energy out of a system? Logically, you have to hit a point where you've removed all the thermal energy you possibly can. A point where the atoms slow down, and down, and down, until they stop moving altogether. This theoretical point of perfect stillness was dubbed absolute zero. And just like that, the race was on. Physicists built incredible machines, liquefying one gas after another: oxygen, nitrogen, hydrogen, pushing temperatures to lows nobody had ever imagined. They were chasing a ghost, a temperature defined not by what it was, but by what it wasn't: the total absence of heat. It was the Irish physicist William Thomson, better known as Lord Kelvin, who formalized the whole thing. He looked at how gases behave, how their pressure drops as they get colder, and followed the trend all the way down to its logical conclusion. He saw that, in theory, the pressure of a perfect gas would drop to zero at a temperature of -273, 15 degrees Celsius. So, he proposed a new scale that started at this ultimate ground floor of reality: the Kelvin scale, where 0K is absolute zero. The picture painted by classical physics was crystal clear. At 0 Kelvin, the universe would enter a state of perfect hibernation. Atoms in a crystal would be frozen in place. Gas particles would fall to the bottom of their container, motionless. It was a world of perfect order and perfect silence. The ultimate off switch. It made perfect sense. It was intuitive. And as we were about to find out, it was completely, fundamentally, and beautifully wrong. The quantum wrench in the works. As physicists got their experiments colder and colder, pushing ever closer to this imaginary finish line, weird things started to happen. The universe, down at these temperatures, stopped playing by the rules. The neat and tidy physics of billiard balls and planets started to fail. It was time for a new rulebook, a stranger and wilder one. This was the dawn of quantum mechanics. And right at the heart of it is a principle so bizarre it single-handedly demolishes the dream of absolute zero. It's called the Heisenberg uncertainty principle. Introduced by Werner Heisenberg back in 1927, the principle sounds simple enough. It says there's a fundamental limit to how precisely you can know certain pairs of things about a particle at the same time. The most famous pair is position and momentum. Momentum is basically how much oomph a particle has, and in what direction. The uncertainty principle says the more you know about a particle's exact location, the less you can know about its momentum. And vice versa. You can never, ever know both perfectly. Now, this isn't a problem with our instruments. It's not like trying to measure a wobbly table with a shaky ruler. The universe itself has a built-in fuzziness. Think about taking a picture of a speeding car. If you use a super fast shutter speed, you get a sharp, clear image. You know its position with pinpoint accuracy. But you have no real clue how fast it was going. It's just a frozen snapshot. Now, try again with a slow shutter speed. The car becomes a long, blurry streak. You have a much better idea of its speed and direction, but good luck telling me exactly where the car was at any specific moment. Quantum particles live in this constant trade-off. Nature enforces a strict bargain. If you want more certainty about a particle's position, you have to pay for it with uncertainty in its momentum. The particle will start to jiggle and vibrate, its velocity becoming a blur. So, what does any of this have to do with absolute zero? Everything. The dream of absolute zero was a state of perfect stillness. An atom that has stopped moving has a precise momentum, zero. And if it's not moving, it also has a precise position, right where it stopped. But the Heisenberg uncertainty principle screams, forbidden. You cannot know both with perfect accuracy. If we try to force an atom to be at absolute zero, its motion has to be zero. That means its uncertainty in momentum is also zero. If you plug a zero into Heisenberg's equation, you get a result that says that zero is greater than or equal to a positive number. And that's a mathematical impossibility. It breaks a fundamental law of the cosmos. To obey the uncertainty principle, if a particle is trapped in a small space like an atom locked in a crystal, its position can be infinitely uncertain. And because its position is confined, its momentum cannot be perfectly zero. It can't be perfectly still. It has to keep moving. It must always have some residual jiggle, some irreducible vibration. Even at the coldest possible temperature. Even at absolute zero. This is the quantum wrench in the works. The classical idea of a perfectly frozen, static universe is impossible. And this leftover, inescapable motion that exists even at absolute zero has a name. It's called *0 energy. The secret energy of everything, 0-point energy, or ZPE, is the absolute lowest energy a quantum system can possibly have. It's the energy of its ground state. If you strip away every last bit of thermal energy you aren't left with zero. You're left with this. It's the universe's baseline hum, the background static that can never be turned off. To get a feel for this, think about a guitar string. Classically, its lowest energy state is when it's perfectly still. But a * quantum guitar string is different. It's never perfectly still. Its lowest energy state, its ground state, is a state of minimum vibration. It's always humming with a tiny, fundamental energy, the ghost in the machine. Another way to picture it. Imagine a marble in a bowl. A classical marble will roll to the very bottom and stop. But a quantum particle is more like a fuzzy cloud of probability. It can't settle at the very bottom, because that would mean having a definite position and a definite momentum, zero, which the uncertainty principle forbids. So instead, it spreads out around the bottom, constantly jittering. These jitters are what we call asterisk quantum fluctuations asterisk, and they are the physical expression of zero-point energy. For a long time, ZPE was just a weird quirk in the math. Did it really exist? Could you prove it? The answer, it turns out, is a huge yes. In a brilliant experiment, scientists cooled molecules down to just a fraction of a degree above absolute zero, where all classical motion should be gone. They then zapped these super chilled molecules with an X-ray, designed to blow them apart. Now, if the atoms were perfectly still before the blast, the fragments should have flown off in a random, uniform pattern. But that's not what happened. The fragments flew off in a very specific, lopsided way. The only explanation was that the atoms were already moving before the X-ray hit them. They weren't still at all. They were jiggling and vibrating in a coordinated dance, exactly as quantum theory predicted. When the researchers ran a simulation of the experiment and artificially turned off the uncertainty principle, the results didn't match. Only when the zero-point jitter was included did the simulation match reality. This was the smoking gun. Scientists were, in effect, watching the shadow of zero-point motion. They had proven that even at the doorstep of absolute zero, matter refuses to be still. The universe that refuses to freeze. The fact that atoms jitter at absolute zero is wild enough, but it's not just a tiny, microscopic quirk. Zero-point energy has huge, real-world consequences. Case in point. The miracle of liquid helium. Take the element helium. When you cool helium gas down to about 4 Kelvin, it turns into a liquid. If you keep cooling it, you'd expect it to freeze solid, just like everything else. But helium is a rebel. As you cool it further and further, down to the coldest temperatures ever achieved, it simply refuses to freeze at normal pressure. Why? Zero-point energy. Helium atoms are incredibly light, and they don't stick to each other very well. Because they're so light, their quantum jitter is extra stronger, in fact, than the weak forces trying to lock them into a solid crystal. The atoms are just too restless to settle down. They literally shake themselves loose, staying liquid no matter how cold it gets. But it gets even weirder. Cool liquid helium below about 2 Kelvin, and it transforms into a asterisk superfluid. Superfluid helium is one of the most surreal things in existence. It has zero viscosity, meaning it flows without any friction. If you swirl it in a cup, it will just keep swirling, forever. It can flow up and over the sides of a container, seemingly defying gravity, and leak through microscopic cracks that would stop any normal liquid. This bizarre behavior is a large-scale quantum effect, and it all exists because zero-point energy prevents helium from ever truly freezing. Case in point 2. The force from nothing. Maybe the most mind-blowing proof of zero-point energy comes from what we think of as its exact opposite: empty space. A perfect vacuum. We think of a vacuum as nothing, but quantum physics says a vacuum is not empty at all. It's a seething, boiling cauldron of activity. Quantum theory tells us that space is filled with invisible fields. Even in a total vacuum, these fields have zero-point energy. They are constantly fluctuating, and out of these fluctuations, virtual particles are constantly popping into existence, only to annihilate each other a moment later. The vacuum is a storm of these phantom particles. Sounds like science fiction, right? But there's proof. It's called the asterisk Casimir effect. In 1948, the physicist Hendrik Casimir came up with an idea. Take 2 perfectly flat metal plates and put them incredibly close together in a vacuum. Outside the plates, virtual particles of all sizes can pop into existence. But between the plates, only particles with wavelengths that fit neatly into the tiny gap are allowed. This means there are more virtual particles, more quantum fluctuations pushing on the asterisk outside of the plates than on the asterisk inside. This imbalance creates a tiny, but measurable, force pushing the plates together. It is, quite literally, a force from nothing. And when scientists finally ran the experiment, it worked. The force was there, tiny but undeniable, proving the vacuum isn't empty. It's filled with energy. The hum of reality. So where does this leave us? We started with the dream of a frozen, silent universe and ended up in a strange quantum reality that can never stop moving. The flaw in the plan to reach absolute zero wasn't a flaw at all. It's a fundamental feature. The endless vibration, the constant hum of quantum fluctuations, isn't a bug in the system. It is the system. This gets even more profound when you learn that what we think of as particles are really just concentrated vibrations in their own underlying fields that fill all of space. There's an electron field, a photon field, a quark field, and so on. And every single one of these fields, everywhere in space, has a zero-point energy. The vacuum of space isn't just humming with a little bit of energy. It's humming with the combined ground state energies of all fundamental fields. In fact, when physicists try to calculate the total amount of this energy, the number they get is basically infinite, a puzzle they're still trying to solve. This leads us to a final, awe-inspiring realization. Absolute zero isn't the end of energy. It's just the moment where you've stripped away all the thermal noise, all the heat, and can finally hear the pure, underlying tone of reality itself. Cooling a system down doesn't turn it off. It reveals its true nature. And this isn't some far-off concept. It's happening right now. The atoms that make up your body, the chair you're sitting on, the air you're breathing, every single particle is constantly jiggling with its own irreducible zero-point energy. You are a collection of trillions upon trillions of tiny oscillators, each humming with the fundamental energy of the cosmos. You are never truly still. Nothing is. The universe doesn't have an off switch. It has a heartbeat. A persistent, quantum vibration that has been going since the Big Bang and will continue for as long as the universe exists. It's the jitter in the heart of every atom, the secret energy of empty space. It is the constant, quiet hum of reality itself. We started by trying to turn reality off, and in the process, discovered what makes it so incredibly alive. The laws of quantum mechanics don't just prevent stillness. They ensure the universe is forever vibrating with a secret, powerful energy. The world is so much stranger and more beautiful than it looks on the surface, and the quest to understand these deep truths is what science is all about. There are countless more mysteries out there, waiting to be unraveled. So for now, just take a moment. That seemingly solid, stable reality all around you is actually a symphony of endless vibration. Every particle, every field, every inch of empty space is buzzing with a faint, primordial energy. The universe isn't silent. If you could listen closely enough, you'd hear its constant, unwavering hum, the eternal heartbeat of existence. And that is a truly mind-bending thought. The cosmic law that forbids stillness. What if I told you that this stillness is an illusion? That the state of true, absolute rest is actually forbidden? There's a fundamental rule woven into the very fabric of reality, a cosmic law that makes it impossible for anything, anywhere, to ever truly be still. To find it, we have to journey from the jitters of empty space to the very edge of our expanding universe. And what we'll uncover might just change how you see everything. It's one of our deepest intuitions, isn't it? That if we take all the energy out of something, if we stop pushing it, stop heating it, block every outside influence, it will eventually settle into a state of perfect, motionless rest. We see it when a spinning top finally wobbles to a halt. We feel it when we hold our breath in a quiet room. It's the ideal of tranquility, the very definition of zero. But this intuition, as powerful as it is wrong. Deeply wrong. As it turns out, reality is fundamentally restless. There is no off switch, no final resting place. The universe, from its smallest bits to its grandest structures, is in a state of perpetual, unavoidable motion. This isn't a fluke, it's a rule. A law without a name, but with consequences that touch everything. To get our heads around this law, we need to peel back the layers of reality, one by one. Our journey starts in a place that seems like it should be the very definition of nothingness. The vacuum of empty space. And right there, in the quiet dark, we'll find our first clue. A ceaseless, invisible tremor that shakes the foundations of the cosmos. The quantum jitters. The smallest scale. When we think of a vacuum, we picture the ultimate emptiness. A box with all the air pumped out, shielded from light, heat, and any radiation. It should be a zone of absolute null, a volume of space containing, well, nothing. Classical physics agrees. In a perfect vacuum, at the coldest possible temperature, you should get a perfect zero. No energy, no particles, no activity. Just pure, featureless void. But the 20th century taught us that the universe doesn't play by classical rules at the smallest scales. When we zoom way in, we enter the strange and deeply weird world of quantum mechanics. And in this world, the idea of a truly empty and static void simply isn't allowed. The reason boils down to one of the most profound principles in all of science. The Heisenberg uncertainty principle. Dreamed up by Werner Heisenberg in 1927, it sets a fundamental limit on what we can ever know about a particle. It says that you can't know certain pairs of properties like a particle's exact position and its exact momentum at the same time. The more you pin down its location, the less you know about where it's going. And the more precisely you measure its momentum, the fuzzier its location becomes. Think of it like trying to snap a photo of a moving car. A fast shutter speed freezes the car in a sharp position, but that single frame tells you nothing about its speed. A slow shutter speed gives you a blurry streak that tells you all about its motion, but its exact position is lost. The uncertainty principle says this isn't about our cameras. It's a built-in feature of reality itself. There's a fundamental fuzziness baked into the universe. So, what does this have to do with empty space? Everything. Imagine a tiny particle sitting perfectly still in a valley. If it were truly still, its momentum would be exactly zero. And if it were at the very bottom, its position would be known exactly. But this scenario, knowing both position and momentum perfectly, is explicitly forbidden by the uncertainty principle. To satisfy the rule, the particle has to keep a little bit of wiggle. It can never fully settle. It must hold onto a minimum amount of energy, a tiny tremor of existence. This rock-bottom energy is called zero-point energy. It's the energy something has even in its lowest possible state, at the coldest possible temperature of absolute zero. This isn't just for particles. It applies to the universe's most fundamental building blocks, quantum fields. Modern physics tells us that reality is made of fields: an electron field, a photon field, one for every particle we know. What we think of as a particle is just a little ripple in its field. In a vacuum, these fields are in their ground state. Classically, that would mean they're flat and have zero energy. But the uncertainty principle won't let them. A field can't have a perfectly defined value, zero, and a perfectly defined rate of change, also zero, at the same time. So, even in a total vacuum, these fields constantly have to jitter. They simmer with what we call quantum fluctuations. Picture the surface of a perfectly calm lake. From far away, it looks flat. But if you could look closely enough, you'd see tiny, shimmering vibrations, ripples appearing and vanishing at random. The vacuum of space is like that. It's a seething foam of energy, with virtual particle-antiparticle pairs constantly popping into existence and annihilating each other in a flash. This isn't just a wild theory. We can see its effects. One of the most amazing confirmations is the Casimir effect. Predicted by Hendrik Casimir in 1948, the idea is simple. Place two perfectly smooth, uncharged metal plates incredibly close together in a vacuum. Outside the plates, virtual particles of all kinds can pop in and out of existence. But between the plates, only virtual particles with specific wavelengths that fit neatly into that tiny gap are allowed. This means there are more quantum fluctuations pushing on the asterisk outside of the plates than on the asterisk inside. The result is a tiny but measurable force pushing the plates together. This force isn't gravity or electromagnetism. It's the vacuum itself, the energy of empty space exerting real pressure. For decades it was just a prediction, but in 1996, a team led by Stephen Lamoureux actually measured this tiny force, and the results were a perfect match. The vacuum isn't empty. It's a physical thing, buzzing with energy. Another clue comes from the fine details of atoms. The Lamb shift, discovered by Willis Lamb in 1947, is a tiny difference in the energy levels of a hydrogen atom that shouldn't exist according to older theories. The explanation? The atom's electron is constantly interacting with the virtual particles of the vacuum, which jiggles the electron just enough to shift its energy. It was another concrete proof that the vacuum is a dynamic, seething place. This background hum isn't just a microscopic curiosity anymore. In specialized experiments, scientists have shown that this quantum noise can affect objects on a human scale. By using instruments as exquisitely sensitive as the 40-kilogram mirrors built for the LIGO Gravitational Wave Observatory, they have been able to measure the tiny jitters in an object's position caused by the quantum fluctuations of light. The law that forbids stillness reaches out from the subatomic realm and literally shakes objects we can see. The atomic dance. The building blocks of you. This cosmic restlessness isn't just out there in the void. It's much closer to home. It's inside you. It's in the chair you're sitting on and the air you're breathing. The law that forbids stillness is at the very heart of matter itself. Let's imagine cooling a single atom down as close as we can get to absolute zero, minus 273.15 Celsius. Classical physics would say its electrons should freeze in their orbits around the nucleus, like tiny planets in a static solar system. Everything locked in place, finally at rest. But once again, the quantum world says, not so fast. The uncertainty principle applies just as much to an electron in an atom. If an electron were to stop moving, we'd know both its position and its momentum, zero, perfectly. And as we know, nature forbids this. So, even in its lowest energy state, an electron can't just stop. It doesn't orbit the nucleus like a planet. It exists as a probability cloud, a fuzzy region of space where it's most likely to be. It is perpetually in motion, its position and momentum forever a blur. This is the atom's zero-point energy. It's the minimum energy the atom must have. Even at absolute zero, the atom vibrates. It jitters. It dances. For a long time, this was just a prediction. How could you possibly see a motion that's so fundamental and subtle? But recently, scientists have found clever ways to witness this quantum dance directly. A team in Germany did this with a molecule called 2-iodopyridine. They blasted these molecules with incredibly powerful and short X-ray pulses from the European XFEL. The pulses were so intense they instantly ripped electrons away, leaving the remaining atomic nuclei fiercely repelling each other. The molecule didn't just break, it exploded in less than a femtosecond, a quadrillionth of a second. By tracking all the flying fragments, the scientists could reconstruct the exact position of its atoms at the moment of the explosion. By doing this over and over, they built a snapshot of the molecule's ground state. And they found the atoms weren't just jiggling randomly. They moved in coordinated, correlated patterns, the specific vibrations predicted by quantum theory. They had captured a direct image of the molecule's zero-point energy in action. This fundamental jittering has real-world consequences. Take helium. Every other element, when cooled enough, will eventually freeze solid. But helium is the lone holdout. Even at absolute zero, under normal pressure, helium stays liquid. Why? Its atoms are so light, and their zero-point energy is so powerful, that the constant quantum jiggling is enough to overcome the weak forces that would otherwise lock them into a solid crystal. The atoms simply refuse to settle down. This restlessness can even trigger bizarre behavior in complex materials. Scientists studying a compound called yttrium iron 2 aluminum 10 found something amazing. As they cooled it to just 0.06 of a degree above absolute zero, it was teetering on the edge of becoming magnetic. Normally, a change like this is driven by heat. But at these cryogenic temperatures, there's practically no heat left. Instead, experiments showed that quantum fluctuations, the inherent jitters of the electron spins driven by their zero-point energy, were playing a critical role in tipping the entire material into a new magnetic state. It was a phase transition driven not by heat, but by the fundamental restlessness of quantum mechanics. Think about what that means. The properties of materials all around us, from liquid helium to complex magnets, are governed by this hidden layer of ceaseless quantum motion. The solidity of a rock is a delicate balance between forces pulling atoms together and the quantum law that insists they always keep moving. Every atom in your body, every particle that makes up the world, is humming with this zero-point energy. You are a collection of trillions of quantum dancers, all vibrating in step with the uncertainty principle. The stillness you feel is just a macroscopic illusion. You are never truly at rest. You can't be. The cosmic expansion, the largest scale. We've journeyed into the heart of the vacuum and found it seething with energy. We've looked at the atoms that build our world and found them dancing to a quantum rhythm. But now, we have to zoom out. All the way out. Past planets, past stars, past our own galaxy, to the unimaginable emptiness between the great cosmic islands of the universe. And here, on the grandest stage of all, we find the law of unrest is more powerful than ever. Back in the 1920s, astronomers like Edwin Hubble discovered that distant galaxies are all moving away from us. And not just that, the farther away a galaxy is, the faster it's receding. This was the first clue to a staggering reality. The universe is expanding. It's important to get the picture right here. The galaxies aren't exploding outwards into a pre-existing empty space. The reality is far weirder. It's the fabric of spacetime itself that's expanding. The classic analogy is a loaf of raisin bread dough rising. Pick any raisin to be our Milky Way. As the dough expands, every other raisin moves away from you. A nearby raisin moves away slowly, but one on the far side of the loaf moves away much faster, because there's more expanding dough between you. From the perspective of any raisin, all the others are rushing away. There is no center. The expansion is happening everywhere. In this picture, the galaxies are the raisins, and spacetime is the dough. The galaxies aren't flying through space. The space between them is stretching, carrying them along for the ride. This cosmic stretch makes true stillness impossible. Imagine you halt an object's motion relative to our galaxy. You even account for our galaxy's movement and bring your object to a perfect standstill relative to the cosmic microwave background, the faint afterglow of the Big Bang, which acts as a universal reference frame. Even then, your object isn't at rest, because the very space it occupies is expanding. The distance between your still object and a distant galaxy will increase by thousands of kilometers in the next second, just because the space between them has stretched. There's no fixed grid to be at rest in. The whole stage is in motion. And here's where it all comes full circle. Where did the vast structures of the universe, the filaments of galaxies and the great voids between them come from? Incredibly, the answer lies in the quantum jitters of the early universe. In the first blink of an eye after the Big Bang, the universe went through a period of insane growth called cosmic inflation. The universe was a sea of high-energy quantum fields, all teeming with quantum fluctuations because of the uncertainty principle. Normally, these are microscopic, fleeting events. But inflation stretched them to astronomical proportions. Tiny, subatomic flickers of energy were suddenly magnified and frozen into the fabric of space. These stretched-out quantum fluctuations became the seeds of everything. The slightly denser regions had slightly more gravity. Over billions of years, they pulled in more and more matter, growing into the first stars, galaxies, and the immense clusters we see today. The vast empty voids are the regions that started out with slightly less density. When we look at the cosmic microwave background, we see a picture of the baby universe. The tiny temperature differences in that light are the direct imprint of those original quantum fluctuations, stretched across the sky. The largest structures in the cosmos are fossils of the smallest, most random events imaginable. The law of unrest isn't just a rule against sitting still. It's the creative engine of the cosmos. Without it, the universe would be a uniform, boring soup. No galaxies, no stars, no planets, and no us. And the expansion isn't stopping. In fact, it's accelerating. Something is actively pushing spacetime apart, a mysterious influence we call dark energy. One of the most tantalizing and troubling ideas is that this dark energy could be the zero-point energy of the vacuum itself. The problem is, when physicists try to calculate how strong this vacuum energy should be, their answer is about 120 orders of magnitude larger than what we observe. It's one of the biggest puzzles in all of science, a sign that we're still missing a huge piece of the picture. The law of change. We started with a simple idea: perfect stillness. We've traveled from the quantum realm to the cosmic horizon, and at every turn, we found that stillness is a myth. At the smallest scales, the Heisenberg uncertainty principle insists that nothing can ever have zero energy, filling the vacuum with a shimmering sea of quantum fluctuations. This zero-point energy is the universe's fundamental background tremor. That same rule forces the atoms in our bodies to vibrate and dance, preventing helium from ever freezing solid and driving strange behaviors in matter near absolute zero. We are collections of trillions of quantum oscillators, humming with motion. And on the largest scale, the very fabric of reality is stretching, carrying galaxies along with it. This grand expansion was itself seeded by random quantum jitters in the first moments of time. The law that forbids stillness isn't just a constraint, it's the architect of the cosmos. From the tiniest particle to the largest galaxy cluster, everything is in a state of perpetual change. Rest is an illusion. This can feel unsettling. It goes against our desire for permanence. But it also offers a more profound perspective. The universe isn't a static, finished thing. It's a dynamic, unfolding process. Change isn't a disruption to the natural order. Change is the natural order. To be part of this universe is to be part of this cosmic dance. You are a temporary, intricate pattern in a universe of ceaseless flow. You're made of stardust from atoms that are themselves vibrating with quantum energy, all surfing the waves of an expanding spacetime that was first stirred by a random quantum fluctuation. The universe doesn't allow for stillness. It demands motion. It demands change. It demands evolution. And in a cosmos governed by this law, maybe the best thing we can do is embrace it, join the dance, and stand in awe of the beautiful, restless creativity of it all. Thanks for joining me on this trip through the restless universe. If this exploration sparked your curiosity, please consider liking the video and subscribing for more journeys into the weird and wonderful nature of reality. And now I have a question for you. Does knowing that everything is in a constant state of flux change how you see your own life? Let me know your thoughts in the comments below. Science just proved empty space is a lie. What if I told you the biggest lie you've ever heard is about nothing? We're taught that space is a void, an empty stage for the cosmic drama, a silent, black nothingness stretching between the stars. It's our very definition of emptiness. When we want to describe something utterly desolate, we say it's like the vacuum of space. This idea makes sense. It feels right. And it's completely, fundamentally, and spectacularly wrong. For centuries, we pictured the universe as islands of stuff, planets and stars floating in a vast, passive ocean of nothing. But the science on this is changing. While the core ideas have been brewing for decades, new evidence is pulling back the curtain on the universe's biggest secret, rewriting the rules of reality itself. What if this nothing is actually the busiest, most chaotic, and most important something in all of existence? What if the vacuum is a seething, bubbling cauldron of energy, constantly creating and destroying matter in the blink of an eye? This isn't science fiction. It's the bedrock of modern physics, a truth being confirmed with hard, experimental evidence. So, get ready, because we're about to journey into the heart of this hidden reality. We'll explore the definitive proof that has shattered our old ideas and show you why the emptiest place you can imagine is, in fact, the most crowded place in the universe. The revelation. The quantum sea. First things first. You have to toss out your everyday intuition. In our world, things are solid and predictable. A box can be empty. A room can be silent. But the quantum world, the rulebook for the fundamental fabric of everything, plays by a completely different set of rules. And in that world, true emptiness is a physical impossibility. Physicists now call what we once thought of as empty space the quantum vacuum. The name change is everything. It shifts the concept from a passive, empty box to something active. Think of the vacuum not as a still, silent container, but as a restless ocean. Even on the calmest day, an ocean's surface is never perfectly flat. There are always tiny ripples, a constant, subtle motion. The quantum vacuum is like that, but infinitely more energetic. It's a landscape of invisible fields, the fundamental forces of nature all shimmering and fluctuating. Think of the fields that run our universe. The electromagnetic field, giving us light, the gravitational field, holding galaxies together, the nuclear fields inside every atom. In the old view, these fields were like silent telephone lines, only active when a particle came along. But quantum field theory, the most successful scientific theory in history, tells us something astonishing. These fields are never truly silent. They are never at zero. Even in the darkest, coldest, most isolated patch of space, these fields are humming with a baseline energy. This is called zero-point energy. It's the energy that remains even at absolute zero temperature, the theoretical point where everything should stop moving. But it doesn't. The universe, at its most fundamental level, can never be still. This isn't a flaw in our measurements, it's a law of nature. The ground state of the universe, its lowest possible energy, isn't nothingness. It's a state of seething, unpredictable, and powerful potential. And from this energy, the universe performs its most incredible magic trick. The cosmic ghosts. Virtual particles. This energy humming throughout space isn't just sitting there. It's constantly doing something that sounds like it was ripped from a fantasy novel. It's spontaneously giving birth to matter. This is possible because of a bizarre quirk of quantum mechanics called Werner Heisenberg's uncertainty principle. In simple terms, it means you can't know certain pairs of things with perfect accuracy at the same time. The more you know about a particle's position, for example, the less you know about its momentum. But another version of this principle relates energy and time, and it opens up a wild loophole in the laws of physics. It says that for incredibly short moments, the law of conservation of energy, the sacred rule that energy can't be created or destroyed, can be borrowed. The vacuum takes full advantage of this cosmic loophole. For fleeting instants, the vacuum can borrow a bit of energy from the future. And thanks to Einstein's famous E=mc², we know energy and mass are two sides of the same coin. With that borrowed energy, the vacuum creates a pair of particles. These aren't the normal, stable particles that make you and me. They're called virtual particles. They erupt into existence as a particle-antiparticle pair, like an electron and its antimatter twin, a positron. They exist for a fraction of a second, a lifespan dictated by the uncertainty principle, before they find each other, annihilate, and pay back the energy debt, disappearing back into the vacuum. The entire universe, every cubic inch of empty space, is a frenetic, boiling foam of these virtual particles popping in and out of existence. For decades, physicists wondered if they were real or just a mathematical trick. How can something be real if it vanishes almost instantly? But science relies on evidence, and recent discoveries are making these ghosts less ghostly than ever. The evidence for the reality of this energetic vacuum is now concrete and powerful enough to move objects in the real world. The ghosts are real, and we have the receipts. The proof: a force from nothing, the Casimir effect. For a concept as wild as a sea of ghost particles, a good theory isn't enough. Scientists needed to find a way to measure their effect on our world. That testable prediction came in 1948 from Dutch physicist Hendrik Casimir. His thought experiment was beautiful. Imagine you take two perfectly smooth, uncharged metal plates and place them in a perfect vacuum. Classically, nothing should happen. They should just float there. But Casimir argued they would be pushed together by the vacuum itself. His reasoning was a direct result of the virtual particle C. In the space outside the plates, virtual particles of all wavelengths can pop into existence. But in the tiny gap between the plates, things are different. The plates act like walls. Only virtual particles with wavelengths that fit neatly into that gap can exist there. Longer wavelength particles are excluded. It's like being on a ship in the open ocean, where waves of all sizes hit you. If you steer that ship into a narrow harbor, only the smaller waves can get in. The big, powerful swells are blocked. The same thing happens to the plates. There are more virtual particles popping into existence on the outside than in the constrained space between them. This creates a pressure difference. The seething vacuum on the outside literally pushes the plates together with more force than the vacuum on the inside. This is the Casimir effect, a physical force generated from empty space. For decades, the effect was too small to measure. But in the 1990s, physicists like Steve Lamoureux finally did it. Using incredibly precise instruments, they brought two surfaces nanometers apart and measured the force. It was real, and it matched Casimir's predictions almost perfectly. And just recently, in 2026, experiments at the Relativistic Heavy Ion Collider, RHIC, provided some of the first direct evidence of these vacuum fluctuations generating real particle-antiparticle pairs, confirming a key piece of this whole puzzle. Science had proven it. Empty space is so full of energy it can physically push things around. The atomic jiggle. The Lamb shift. The Casimir effect was a sledgehammer of a proof, but the vacuum's influence also reaches into the very heart of matter. The next piece of the puzzle is called the Lamb shift, and it was discovered in a flurry of post-World War II activity. The story starts with the simplest atom, hydrogen. One proton, one electron. Quantum theory in the 1930s made incredibly precise predictions about the energy levels an electron could have. Think of them like rungs on a ladder. The theory said two particular rungs, the 2s and 2p states, should have exactly the same energy. But in 1947, a year before Casimir's proposal, physicist Willis Lamb used new microwave tech to measure these levels with unprecedented precision. He found they were not the same. There was a tiny, shocking difference. It was as if something was giving the electron an extra nudge. The answer, once again, was the quantum vacuum. Physicists like Hans Bethe realized the electron isn't orbiting in a peaceful void. It's swimming through that chaotic sea of virtual particles. It's constantly being buffeted and jostled. Imagine a small boat on a lake. The old theory assumed the lake was calm. But the new understanding revealed the lake was constantly being pelted by invisible raindrops. The virtual particles making the boat jiggle. This jiggling smears out the electron's position, slightly changing its interaction with the nucleus and, therefore, its energy. The calculations, including this vacuum interaction, matched Lamb's experimental results perfectly. The Lamb shift proved the vacuum is an active participant in how every atom works. The empty space between atoms is part of what makes an atom an atom. The grand implication. Seeding the cosmos. So, we've seen the proof in the lab, pushing plates and jiggling atoms. But does this chaotic sea of particles affect the universe on the grand, cosmic stage? The answer is the most profound yes imaginable. The buzzing, fluctuating reality of the quantum vacuum is the very reason we are here. Let's travel back to the first fraction of a second after the Big Bang. Our best model says the universe underwent a hyper-fast expansion called cosmic inflation, swelling from smaller than a proton to the size of a grapefruit in an instant. Now, that tiny, pre-inflation universe was an incredibly hot soup of energy, and just like today's vacuum, it was alive with quantum fluctuations, tiny, random variations in density. In a normal universe, these would average out to nothing. But the universe wasn't normal. It was inflating at a mind-boggling rate. As it expanded, it grabbed these tiny, fleeting quantum fluctuations and stretched them to astronomical sizes. A subatomic wiggle became a vast region of space that was slightly denser than its surroundings. The randomness of the quantum world was frozen into the fabric of spacetime. After inflation, these denser regions had slightly more gravity. Over billions of years, they pulled in matter, forming the first stars, then galaxies, then the massive galaxy clusters we see today, all arranged in a magnificent cosmic web. The less dense regions became the great voids in between. The entire large-scale structure of our universe is a direct, magnified photograph of quantum fluctuations from the beginning of time. Think about that. The reason the Milky Way is here, and not somewhere else, can be traced back to a random quantum event at the dawn of time. You are living inside a fossil. We are all living inside the result of one giant, amplified quantum fluctuation. Without the unemptiness of the vacuum, the early universe would have been perfectly smooth. No structures would have ever formed. No galaxies, no stars, no planets, and no us. The dark mystery, fueling the expansion. The vacuum's role as the seed of all structure is staggering, but its influence might also be the key to one of the biggest mysteries in science: the accelerating expansion of the universe. In the late 1990s, astronomers measuring distant supernovae discovered something revolutionary. The expansion of the universe isn't slowing down due to gravity, as everyone expected. It's speeding up. Something is pushing space apart, a mysterious anti-gravity force dubbed dark energy. It seems to be an intrinsic property of space itself, making up nearly 70% of the universe. But what is it? The most obvious suspect was right there in front of us. The energy of the quantum vacuum. This zero-point energy, according to Einstein's theories, would exert a repulsive force, pushing space apart exactly what we observed. It seemed like a perfect match. There was just one problem. A catastrophic problem. When physicists calculated the theoretical amount of energy the vacuum should have, the number was absurdly, impossibly large. If the vacuum were that powerful, the repulsive force would have blown the universe apart in the first fraction of a second. Atoms would have been instantly shredded. When you compare the theoretical prediction with the observed value of dark energy, the numbers are off by a factor of 10 to the power of 120. That's a 1 with 120 zeros after it. This is, without exaggeration, the worst theoretical prediction in the history of science. It's called the cosmological constant problem. So we're left with a tantalizing puzzle. The vacuum seems to be the perfect candidate for dark energy, but our best theory for it is wrong by an amount that boggles the mind. Clearly, something fundamental is missing from our understanding. Solving this is one of the holy grails of modern physics. Giving substance, the Higgs field. We've seen that space is a teeming sea of energy that seeds galaxies and drives cosmic expansion. But the story gets even more personal. The properties of space are the reason you have substance. The reason you're a solid object and not a flash of light is due to another invisible field that permeates every point in the universe. The Higgs field. Think of the quantum vacuum as the lowest energy state of all fundamental fields combined. One of the most important is the Higgs field. In the 1960s, our standard model of physics worked beautifully, but only if all fundamental particles were massless, which they obviously aren't. In 1964, physicists like Peter Higgs and François Englert proposed a solution. They theorized an invisible energy field that is always on, everywhere. They argued that particles aren't intrinsically massive. They get mass by interacting with this field. Imagine the Higgs field is a kind of cosmic molasses filling all of space. Some particles, like photons of light, don't interact with it at all. They zip right through, remaining massless. Other particles, like electrons, feel a bit of drag as they move through the molasses. This resistance to being accelerated is what we perceive as mass. A heavier particle, like a top quark, is like trying to wade through thick mud. It interacts very strongly with the field. So, the emptiness of space is what gives you substance. Without the Higgs field, all particles would be massless, flitting about at the speed of light. The universe would be a fleeting soup of energy with no stable structures, no planets, and no people. For nearly 50 years, this was just a theory. The proof would be to find its associated particle, the Higgs boson. On July 4, 2012, scientists at the Large Hadron Collider announced they had found it. The discovery confirmed that space is filled with a field fundamentally responsible for mass in our universe. We started with the simple idea that space is empty. We've seen how that comfortable lie has been dismantled. The picture of a silent void has been replaced by the reality of a dynamic, seething quantum vacuum. We learned that thanks to the uncertainty principle, space is buzzing with a baseline energy and a constant foam of virtual particles popping in and out of existence. We saw the proof. The Casimir effect, a force from nothing pushing plates together, and the Lamb shift, the vacuum's fingerprint on every atom. We zoomed out and saw how its ancient jitters seeded every galaxy in the cosmos. We confronted the mystery of dark energy, where the vacuum is the best suspect for the universe's accelerating expansion, yet presents the biggest puzzle in physics. And we brought it home, learning that the Higgs field, another property of the vacuum, is what gives our bodies mass and substance. The empty stage is a lie. The stage itself is the most important actor in the cosmic drama. The nothing between the stars is the source of forces, the seed of galaxies, the origin of mass, and the engine of cosmic expansion. The next time you look up at the blackness of the night sky, you're not looking at an absence. You are looking at the hidden machinery of existence itself. And the story is far from over. The puzzles, like the vacuum catastrophe, tell us how much we still have to learn. The universe, it turns out, is a secret it's only just beginning to reveal. We've journeyed from the subatomic to the cosmic, all to understand the true nature of nothing. It raises a huge question for our future. If this vacuum energy is as powerful as theory suggests, and humanity one day learns to tap into it, what's the first thing we should do with that power? Let me know your thoughts in the comments below. And if you want to keep exploring the biggest secrets of the universe, make sure to subscribe so you don't miss our next journey into the unknown. The paradox of absolute zero: why motion never dies. Scientists once had a simple, elegant dream: to cool something down so much that every single atom would freeze perfectly in place. They thought they could reach the ultimate end of all motion. But as they got closer, they didn't find the perfect stillness they were looking for. Instead, they discovered a fundamental law of the universe, a law that makes perpetual motion not just some bizarre possibility, but an absolute necessity. What they found was the paradox of absolute zero. Ever wonder why we can get incredibly close to absolute zero, but never actually reach it? It's easy to think it's just a technology problem, like we just need to build a better refrigerator, right? Well, that's not it. The quest for the coldest temperature possible isn't just a race to a number. It's a journey into the heart of reality itself. A journey that starts with an idea: we all get cold means slow, colder means slower, and coldest must mean stopped, and ends with a shocking twist that turns our entire understanding of existence on its head. By the end of this, you'll see that motion isn't just something that happens in the universe. It's a mandatory, unbreakable rule baked into the code of reality. The classical dream of ultimate stillness. Let's start with a concept we all feel in our bones: temperature. On a warm day, the world feels alive, buzzing with energy. On a cold day, things seem to slow down, becoming quiet and still. For centuries, this was the bedrock of physics. Scientists pictured matter as a swarm of tiny particles, atoms and molecules in constant, frantic motion. The faster they jiggled and bounced, the hotter the substance. The slower they moved, the colder it got. It's a beautifully simple model. Heat is just the kinetic energy of these particles. Add energy from a flame, and they speed up. Take energy away in a freezer, and their chaotic dance becomes a gentle sway. The logic seemed flawless. Hot is fast. Cold is slow. From this simple idea, a huge question sparked in the minds of 18th and 19th century scientists like Guillaume Amontons and Lord Kelvin. If you can keep removing heat, what happens when you remove all of it? Logically, you'd eventually reach a point of no return. A point where the particles have zero kinetic energy left to give. They would, in theory, grind to a complete and utter halt. This theoretical endpoint was named absolute zero. It was defined as zero on the Kelvin scale, a mind-numbing -273, 15 degrees Celsius, or -459, 67 degrees Fahrenheit. In this classical picture, a perfect crystal, at this temperature, would have its atoms locked into their lattice positions, absolutely motionless. No vibrations, no rotations, no thermal energy at all. Entropy, the measure of disorder, would fall to its absolute minimum. It was the dream of ultimate stillness, a silent, frozen snapshot at the very bottom of temperature. This wasn't just some academic thought experiment. It was the next great frontier. The race to absolute zero became a massive scientific quest in the early 20th century. Labs across the globe, led by pioneers like Heike Kamerlingh Onnes, pushed the limits of refrigeration, liquefying one gas after another until they finally conquered the most stubborn of all: helium. With every fraction of a degree they shaved off, the world watched, wondering what they'd find in that realm of extreme cold. They dreamed of a world where nature's laws would be laid bare, stripped of the messy fuzz of thermal motion. But as they crept closer to that final, absolute point, the universe started hinting that their neat, logical dream was about to crumble. They were about to hit a wall, not a wall of technology, but a wall built into the laws of physics itself. The first wall. The infinite staircase of thermodynamics. The first clue that absolute zero was more than just an engineering puzzle came from the very laws that defined it. Thermodynamics. Specifically, the third law. While the first two laws deal with energy and entropy, the third law describes what happens as you get near absolute zero. It states that the entropy of a perfect system approaches a constant minimum value as the temperature approaches absolute zero. But hidden in this law is a cruel, almost taunting, implication. It's impossible to reach absolute zero in any finite number of steps. Let's use an analogy. Imagine you're trying to bail water out of a leaky boat. At first, the boat is full of water, it's hot, and you can use a huge bucket to scoop out a ton of water at once. Easy. But as the water level gets lower, you have to switch to a smaller cup. You're still making progress, but each scoop is less effective. The job gets harder. Now, imagine that the closer you get to an empty boat, the smaller your tool becomes. You go from a cup, to a spoon, to an eyedropper. The closer you get to that very last drop, the more infinitesimally small your tool gets, and the more effort it takes to remove a tinier and tinier amount. You can get unbelievably close 99.999% of the way there, but you can never perform the final action that removes that last, elusive drop. Cooling a substance to absolute zero is exactly like this. Every cooling method we have works by removing heat. But as the system gets colder, it has less and less heat to give away. The efficiency of any cooling process plummets the colder you get. You're putting in way more work to extract way less energy. Think of it as a staircase where the steps get smaller and smaller as you go down. Each step takes you closer to the ground floor absolute zero, but the steps become so infinitesimally tiny that you could take an infinite number of them and never actually touch the floor. It's an asymptotic limit. You are always one vanishingly small step away. And scientists have gotten tantalizingly close, achieving temperatures of mere picokelvins trillionths of a degree above absolute zero. But they can never take that final, impossible step to 0K itself. For a long time, this thermodynamic barrier was seen as the main reason absolute zero was off limits. It told us that we couldn't get there. But this is where the story gets really weird. The paradox isn't just that we can't reach absolute zero. The deeper truth is that even if we could magically bypass thermodynamics and land at 0 Kelvin, the universe has another, stranger rule waiting for us. A rule that says even with zero thermal energy, the atoms would still be moving. The dream of perfect stillness wasn't just impossible to reach, it was wrong from the start. The real barrier wasn't thermodynamics. It was quantum mechanics. The deeper truth. The quantum revelation. Alright, let's pretend for a second. We did it. We built the ultimate refrigerator, ignored the third law of thermodynamics, and now we have a perfect crystal of atoms sitting at exactly 0 Kelvin. All thermal energy is gone. According to classical physics, the story ends here. The atoms should be perfectly still. But they're not. They're still jittering. They're humming with a strange, ghostly energy that can never be removed. Why? Because we've just walked into the quantum realm, where the rules are completely different. The culprit behind this mandatory motion is one of the pillars of quantum mechanics: Werner Heisenberg's uncertainty principle. The uncertainty principle isn't about our tools being clumsy. It's a fundamental, non-negotiable property of the universe. It states there's a built-in trade-off between certain pairs of a particle's properties, the most famous pair being its position and its momentum. You cannot know both the exact position and the exact momentum of a particle at the same time. The more you pin down one, the fuzzier the other becomes. Think of it like this. If you could point to the asterisk exact location of a wave's crest, its position, the wave itself is spread out, making its direction and speed, its momentum, totally undefined. If you see a long, rolling wave with a clear direction, you can't say it exists at just one single point. Now let's apply this to our atom at absolute zero. For an atom to be perfectly still, two things would have to be true. First, its momentum would have to be exactly zero. That's what not moving means. And second, for it to be in a crystal, it would have to be at a specific, known spot. We'd know its position perfectly. According to Heisenberg, that's a cosmic impossibility. If you know the momentum is exactly zero, the uncertainty principle says the particle's position must be infinitely uncertain. It could be literally anywhere. And if you know its position is fixed in that crystal, its momentum must be uncertain. It cannot be exactly zero. If it were, you'd be breaking a fundamental law of reality. This forces a wild conclusion. Since a particle can never have both zero momentum and a fixed position, it can never be truly still. It must always have a minimum amount of energy, a baseline hum of motion it can never go below. This irreducible, inescapable energy is called zero-point energy, ZPE, asterisk. Zero-point energy is the heart of the paradox. It's the energy a quantum system has even in its lowest possible energy state, its ground state, at absolute zero. This energy doesn't come from heat. It comes from the quantum jitters baked into the fabric of spacetime itself. The universe, at its most basic level, is a sea of fluctuating energy fields that are always on, causing particles to jiggle constantly, even in the coldest, darkest void. The idea first gained traction when scientists like Albert Einstein and Otto Stern, in 1913, noted that experimental data for molecules at low temperatures didn't fit classical theories. The molecules seemed to hold onto some leftover vibrational energy, even as they approached absolute zero, the first big clue that motion doesn't die. So, the ultimate stillness scientists dreamed of is forbidden. To stop all motion would be to break the universe. The particles in our make-believe crystal at 0 Kelvin are locked in an eternal, subtle dance, choreographed by the uncertainty principle. They are forever vibrating with an energy that isn't thermal, but purely quantum. This wasn't a failure to reach a goal. It was the discovery of a much, much weirder reality. The paradox is complete. The very condition for absolute zero no thermal motion revealed a universal law that makes perpetual motion mandatory. The new frontier. The weird consequences of endless motion. The discovery of zero-point energy wasn't a dead end. It was a key that unlocked a door to a bizarre new realm of physics, where the rules we take for granted get bent and broken. The fact that motion never dies isn't a bug, it's a feature. And this feature gives rise to some of the most mind-bending phenomena we know of. Superfluids, superconductors, and Bose-Einstein condensates. Let's start with superfluidity. Take helium-4. Like anything else, as you cool it, it turns from a gas to a liquid. But if you keep cooling it under normal atmospheric pressure, something strange happens. It refuses to freeze solid, no matter how cold it gets. The reason? Zero-point energy. The zero-point vibrations of the helium atoms are so energetic that they overcome the forces that would normally lock them into a solid crystal. The atoms are just too jittery to freeze. They stay in a liquid state, constantly sliding past one another. But it gets weirder. Cool that liquid helium below 2 17 Kelvin, and it transforms into a superfluid, a liquid with absolutely zero viscosity or internal friction. If you swirl a cup of superfluid helium, it will theoretically keep swirling forever. This allows it to do impossible things, like flow up and over the sides of a container, seemingly defying gravity. It can also seep through microscopic cracks that not even a gas could pass through. This is because all the atoms start acting in perfect unison, as a single quantum entity, flowing without losing any energy. Then there's superconductivity. This is the flow of electrons with zero electrical resistance. In some materials, when cooled way down, electrons pair up into Cooper pairs. These pairs then move through the material's atomic lattice in a coordinated quantum wave, completely ignoring the impurities and vibrations that would normally cause resistance and heat. A current started in a superconducting loop could flow for billions of years with no power source. This is deeply connected to the quantum jitters of the lattice itself. And we've seen this quantum dance. In 2018, researchers used an incredibly sensitive device to directly image these quantum fluctuations in a superconductor. They saw bubbles and puddles of different quantum phases flickering in and out of existence. They were literally watching the static of zero-point energy. More recently, in 2024, a team used high-intensity X-ray lasers to take snapshots of molecules exploding at cryogenic temperatures. The fragments flew off in a specific pattern that could only be explained if the atoms were already vibrating from zero-point energy before the explosion. They captured the eternal dance, proving the molecule was never truly at rest. Finally, there's the Bose-Einstein condensate, Beck. Often called the fifth state of matter. To make one, you cool a gas of atoms to just billionths of a degree above absolute zero. At these insane temperatures, the atoms wave like nature expands until they all overlap. They lose their individual identities and merge into a single quantum object, a giant superatom. Yet even in this state of ultimate coherence, the superatom is not motionless. It still has zero-point energy. It is the most striking demonstration of quantum mechanics made visible, the ultimate ground state, still humming with the irreducible energy of the quantum vacuum. This journey from a simple dream of cold to the bizarre reality of the quantum world shows just how deep and strange the universe really is. So, what broke your brain more, the idea that atoms can never stop moving, or that this endless motion creates impossible things like superfluids? Let me know in the comments. And if you enjoy unraveling the mysteries of the cosmos, make sure to like and subscribe for more journeys into the beautiful weirdness of reality. The universal hum. So, where does this leave us? We started with a simple, classical dream of reaching ultimate cold and perfect stillness. We pictured a universe that could be turned off, silenced, and examined in a state of perfect rest. But the universe had other plans. First, it built a thermodynamic wall, that infinite staircase that makes reaching the ground floor of absolute zero practically impossible. Then, it revealed that the ground floor isn't solid ground at all. It's a trampoline, constantly vibrating, driven by the laws of quantum existence. Heisenberg's uncertainty principle says that to exist is to be uncertain, and to be uncertain is to be in motion. Perfect stillness isn't just unreachable, it's illegal in this universe. This is the paradox of absolute zero. The quest to eliminate motion led us straight to the discovery that motion is inescapable. But this isn't a story of failure. It's a story of profound discovery. The zero-point energy that forbids stillness is the very engine that creates the most exotic phenomena we've ever seen. Now, zoom out from our labs, past our planet, into the coldest, emptiest voids of intergalactic space. Even there, where the temperature is just a few degrees above absolute zero, the universe isn't silent. The vacuum of space itself isn't empty. It fizzes with quantum fluctuations, a sea of virtual particles popping in and out of existence, all driven by that same zero-point energy. The entire cosmos is humming. There is no off switch. Motion never dies. Even in the deepest silence and the most profound cold, there is a constant, quiet, quantum dance, the eternal heartbeat of reality itself.